Okay, hey, welcome everybody. It's great to see so many of you here. It's my great pleasure to open the CWI Lectures 2022. So it's great to see Monique here, who is actually these whole lectures are actually dedicated to Monique Laurent, because she received the CWI Fellow actually last year in November, and so this series of lectures is actually held in honor of Monique. There will be more kind of discussed during the day. But for now, it's just like my great pleasure to open this. And the theme of this year's lectures is actually algebraic and geometric methods in optimization. And I'm very happy that we actually put together, I think, a very nice program. We have 4 excellent speakers from all over the world who will kind of give presentations on this exciting topic. So I'm very much looking forward to the lectures. But maybe let me just briefly mention, my name is actually Guido Schäfer. I'm a senior researcher at CWI and a scientific member of the management team. And together with my colleague, Daniel Dadouche, we had actually the opportunity to organize this day, to set up this day. And we're, I guess, excited about the program, looking very much forward to it. And we'll hear more about this thrilling topic of algebraic and geometric methods in optimization. I don't want to kind of take too much time, because indeed the opening speech will be given by Ton de Cook, CWI director. So I'd like to give the floor to you, Ton, to have the welcome speech.
Thank you, Guido. Well, maybe welcome again to some, to CWI, the Dutch National Institute on Computer Science and Mathematics, founded in 1946 as Mathematisch Centrum, Center for Mathematics. And as it happens, next year it will be 40 years ago that Mathematisch Centrum changed name for Centrum voor Wiskunde en Informatica, CWI. So maybe there's another celebration in store. I don't know, we haven't thought about this yet. But of course, computer science has been part of CWI's work ever since the 1950s as computers emerged. These are the CWI lectures of 2022, and they are organized yearly by one of the CWI research groups and enabled to share the state of the art on a research topic of great interest to this group and to science in general. Another regularly recurring aspect of the CWI lectures is that they are dedicated to a recently appointed CWI Fellow, in this case Monique Laurent. I found out that it even goes that far that the CWI lectures change names and become, on one occasion, CWI Lectures. Something like CWI Laurentius or so. But you hear this is not the way it works for today. CWI Fellow is something of CWI itself, and we express by this appointment our appreciation and gratitude to someone who over a long period of time has given efforts and contributions to science and also to service to CWI and society. Also, you don't want to hear all this probably in Monique, but I just have to mention this. You are the first female CWI Fellow, and this will always be the case. I'm a mathematician by background, so. No, I know that Monique doesn't like to be applauded to, so I will leave it at this. This year's CWI lectures are the start of the last part of the CWI semester program on polynomial optimization and applications. So many of you have visited CWI 3 times since end of August, where I include the Dutch Day on Optimization. It should be the 4th time, but it has been 3 times since. Yeah? I hope that these intense days of exchanging research ideas and research results have created a bond between all participants that can be a common ground for further collaboration. And this should yield much needed further progress in your field as challenging problems of various kinds await solutions. Probably the most pressing problem for the foreseeable future is climate change. Solutions to this problem require a multidisciplinary approach, but at the heart of each of these monodisciplines involved are models. Whether models that describe energy generation and distribution, or models that describe food chains, or models that describe the behavior of economic actors. And each of these models contain objectives and constraints. And most of these models are nonlinear by nature, for example, and uncertainty must be taken into account. In the introduction to this program, I saw several other concrete problems mentioned and scientific fields that use optimization such as operations research, control theory and machine learning. And it's interesting to note that in particular machine learning seems to be more and more an element of optimization methods, and at the same time we need research like that of this community to understand these machine learning methods and make them more efficient and effective. So, today is an important day for CWI, for the future of CWI, and as we hope that many of you become regular visitors of our institute to work together on challenging research problems. Let me end by thanking Monique, Simon Taylor, Job Briet and Bert Zwart for setting up the semester program together. And I would like to thank Guido Schaefer and Daniel Daduche for setting up this day in honor to Monique. And I end by basically saying that I look forward to the presentations of Etienne de Klerk, Frank Valentin, Amir Ali Ahmadi and Rekka Thomas. I know you are also waiting for these lectures, so I thank you and give the floor back to Guido.
Without further ado, I'd like actually to introduce our first invited speaker, Etienne de Klerk. Etienne is full professor at Tilburg University since 2009 at the Department of Econometrics and Operations Research. And he has been at different places before that position, actually in the Netherlands and also abroad. So from 1998 to 2003, he was an assistant professor at the Delft University of Technology, where he also completed his PhD. And then in 2003 to 2005, he was an associate professor at the University of Waterloo in Canada. And somewhat overlapping from 2004 to 2008, he was an associate professor at Tilburg University. And then he was promoted to full professorship in 2009. He also was a full professor at the Nanyang Technological University in Singapore. This was from 2012 to 2013. And he's also part-time affiliated with Delft University of Technology. So Etienne is an expert in mathematical optimization, in particular in semi-definite programming, as we'll also see from your talk. He has written a monograph on aspects of semi-definite programming that appeared in 2002. And Springer is by now a standard textbook that we read. He's an associate editor of the SIME Journal on Optimization, the Infamous Journal of Operations Research, and he's also been a guest editor of Mathematical Programming B. So Etienne received also various awards and grants, among which Canadian Foundation for Innovation's New Opportunities Fund, a prestigious VD grant from NWO, the Dutch Research Council, an ENV Groot or XL grant on machine learning and optimization, Optimal. And in 2017, he was also awarded the Best Paper Prize from the Springer Journal Optimization Letters. So it's our great pleasure, Etienne, to have you here. Many thanks for giving your talk. So please, Etienne, the floor is yours.
Thank you, Guido. Sound check, is the mic working? Yes. Yes, thank you very much. So thank you again, Guido, for the invitation. Also, Daniel, for not taking no for an answer. It's a great pleasure to speak at this nice event in honor of Monique Laurent. I indeed submitted a very ambitious title, talking about proving inequalities and talking about iterative methods in general. But what I would like to do is just focus my thoughts on one specific method that's easy to understand. And so then it's easier to parse some of the results. So this method dates back to Cauchy, and it's called the gradient method. And it's particularly simple. I think everybody who's ever had a course in nonlinear optimization will have studied this method. So the idea is that we aim to minimize some input function f. It's a function of n variables, a real valued function. We are given a starting point in Rn, which I call x1. We are given a number of steps that we wish to perform of this iterative method, capital N, and we are given step lengths, which are just positive scalars. And then we are doing this following iterative process. The new point xk plus 1 is the old point xk, updated by this second term here, which is just the minus gradient at the old point xk minus the gradient of f at the old point, and then multiplied by this step length tk. Okay, so this is a very simple iterative method that aims to minimize a function of n variables. So the method is due to Cauchy, and he studied this near the end of his career in 1847. And he described it in a very short note, a 3-page note that appeared in that year. And you can easily translate the French. It says it's a method, a general method for the resolution of systems of simultaneous equations. So in modern language, we would call this a nonlinear regression problem, or a nonlinear least squares problem. And what Cauchy said about this in his note is that about the convergence is the new value of the objective after one step is not the minimum. One can deduce, again, proceeding in the same way, a new value still smaller. And so continuing smaller and smaller values will be found, which will converge to a minimum value. So basically all he's saying, it's a descent method. So the function value will decrease or not, will be non-increasing at every step. And it's bounded from below because it's a nonlinear least squares problem. So it will converge to something, but we don't know what. So that's, Cauchy left it there. And if you want to make more precise statements, you will have to limit yourself to certain classes of functions. It's just too general to consider all differentiable functions f that you might encounter as input. So the class of objective functions where one can say interesting things is called the class of bounded curvature functions, or functions of bounded curvature. And these functions are also known as hypoconvex functions. So I will explain to you what these objects are. But first of all, a special case of them are the L-smooth functions. And for our purposes, I'm only going to speak about continuously differentiable functions. So because we are studying the gradient method, we need the gradient, and I'm going to assume the gradient is a continuous function. But if the gradient is in fact Lipschitz continuous, then we speak about an L-smooth function. Okay, so this is the Lipschitz continuity condition for a function, and so a function that satisfies this gradient condition is called L-smooth. And then we are minimizing the function, and so it makes sense for us to assume at least that we will have a global minimizer. I will denote it by x star, and it has a corresponding function value f star. So we are trying to compute the values, the vector x star and f star if possible, and we will see how well the gradient method performs with these considerations in mind. So there's a very nice property of L-smooth functions that we can always use. Is called the descent lemma, and it basically tells us that the distance from the optimal value of the function at the point x is lower bounded by this expression here. So basically, the way you prove this is by showing with a simple exercise in calculus that you can always take a step in the negative gradient direction of length 1 divided by L, and then you can always get at least this much reduction. Okay, so this is a general inequality that's true for all L-smooth functions, and this is something that we are going to use. So now moving to the larger class of bounded functions of bounded curvature, we are staying with continuously differentiable functions. So we say a function has maximum curvature if the function here, which is just the norm of x squared times the constant L divided by 2 minus f, is in fact a convex function. Okay, so this might not be too intuitive, but this corresponds to a function being L-smooth. So the next thing that we can require is, so this is the first was the maximum curvature. Now the minimum curvature a function is said to have minimum curvature mu if we can subtract some quadratic function from f and still obtain a convex function. So in particular, we require that mu is at most L, but it can take negative values as long as these are finite negative values. So in particular, what we can see, if mu is equal to 0, this implies that f is a convex function. So this includes the class of convex functions if mu is equal to 0. And we will have a notation for this class of functions of bounded curvature, which again are also called hypoconvex functions. So we have these parameters mu for the minimum curvature, L for the maximum curvature, domain is Rn, so we have this notation f mu L Rn. If we have mu is 0, we already said we're speaking about convex functions. The L we said corresponds to L smooth. And if mu is minus L, so then we are talking exactly about the class of L smooth functions. And if our function, in addition to being continuously differentiable, is also twice continuously differentiable, then it has a Hessian. And then the condition f belonging to this class is the same as saying that the spectrum of the Hessian lies between mu and L. So all the eigenvalues of the Hessian lies between these two values. Okay, so this is for me a very easy way to think about hypoconvex functions. These are the functions, if you think about twice continuously differentiable, where the eigenvalues of the Hessian lie inside a certain interval. So one other important thing that we should notice right away is that these functions are defined in terms of this norm. And if we change the norm, then we change the class of functions. So these functions are not invariant under changing the norm, or in our case, we are going to work with induced norms. So if we change the underlying inner product on the space, we change the function class. This is also important to remember. Okay, so what tool am I going to use to analyze the method of Cauchy for these hypoconvex functions? So the tool that I want to describe, because it's quite fits with the research interests of this meeting, namely semi-different programming, was pioneered by Mark Taboul and his PhD student at that time, Yoel Drori. This was in 2014. And their idea was to formulate the problem of finding the worst case input for the gradient descent method as the analytic solution of some optimization problem. Okay, so once again, we have the Cauchy algorithm. The input is some function f, and we're going to restrict it to this class. And we're asking ourselves, what is the worst case input? Okay, so for which function gives the worst case performance of the Cauchy method? And their insight was sometimes you can write this problem of finding the worst case input as a different optimization problem which is tractable. And in particular, it's a so-called semi-different programming problem. Okay, so what is the idea? So let's just try and see how far we get if we just try to formulate the problem that finds the worst case input to the Cauchy algorithm. So we can think of different objectives that we might have if we perform n iterations. So we would like the gradient to converge to 0, for the gradient norm of the iterates to converge to 0. So we can say the worst case scenario is obtained if f is such that the gradient after n steps is a maximum, or if the distance in function value from optimality is a maximum, or if the distance from the minimizer, the global minimizer, is a maximum, or sometimes it's appropriate to use a weaker notion of the convergence of the gradient norms to 0. So this corresponds to just saying that there would be a subsequence of points for which the gradient norm converges to 0. Okay, so these are all legitimate possible criteria for defining what we understand as worst case performance for the Cauchy method. And then we would like to add some constraints. First of all, we need to bound the problem so that otherwise we will not get interesting solutions. So we're just going to introduce some parameter, fixed parameter delta, and say that the function value at the starting point minus the optimal value is bounded by this. Okay, so this is without loss of generality. So we just consider the class corresponding to a given delta. Then also we say that, okay, we're going to generate more points, x2 up to xn plus 1 after n iterations. And these points have to correspond to points generated by the gradient descent algorithm with respect to our function that gives us the worst case performance, and with respect to our chosen starting point. So our starting point is going to be a variable in finding the worst case input as well as the function. So it's a bit confusing to understand this optimization problem. The variable is the function from this class and the starting point. The givens are these parameters just to bound the starting situation. And then these parameters for my class of functions, the mu and the L. And then the number of steps I want to take and the step lengths that I'm going to use. These are all the inputs, or these are the parameters. So it's a difficult optimization problem because it involves a variable that lies in infinite dimensional space, this set of functions. The set is a very complicated set. It has basically no nice properties. So we do not know how to deal with that. So we would like to transform this optimization problem into something more tractable. And then the key idea is that this can be reformulated as a semi-definite programming problem, which is tractable, by representing this function class via interpolation. So somehow we're going to bring this infinite dimensional space down to finite dimensions by changing this membership problem into an interpolation problem. Okay, so how does this interpolation problem work? So the idea is that if we are given an index set, it's denoted by I, and these index set are just given some data triples. So we're given some vectors xi, some more vectors gi, and some scalars fi. And basically we are asking if this data corresponds to a function from the class that we're interested in. So the x will correspond to points in the domain. The gi's will correspond to the gradients at those points, and the fi's we would like to correspond to the function values. So given such data, the question is, do these things correspond to some function f in our class of interest, in the sense that these fi's are just the function values, and these given gi's are just the gradients at the given points xi. Oops, so this s has changed from the I has changed into an S. My apologies. Okay, so this is the interpolation question. And if the data can be interpolated by a hyperconvex function from our class, then we say that the data is f mu L interpolable. Whoa, mouthful. Okay, so here is the key result, which is really the main tool that is used in this reformulation. This is an interpolation theorem that was developed over a number of years. And this was due to a group at Louvain-la-Neuve, François Glenier, Julien Hendricks, and at that time, Adrian Taylor, their PhD student. So they had 2 papers about this, and this has been finalized in this form I'm showing here just this year by François Glenier with the next generation of researchers. And what this theorem says is this condition that the data set can be interpolated by something in our function class is the same as some finite set of inequalities holding for this data set. So basically, we can answer the question with certainty whether the data can be interpolated by a hyperconvex function by just checking a finite set of inequalities. So basically, for all points, all distinct points I and j in our all distinct indices I and j in our index set, we just have to check that this inequality is true. So where does this inequality come from? Well, this just corresponds to a known inequality for hyperconvex functions. So just to make it a little bit easy for ourselves, if we think about convex functions, then mu is 0, so we don't lose these terms. We lose this part here. And then if we just let L go to infinity, because the theorem is actually true also for L infinity, then everything on the left-hand side becomes 0. And we just left with this thing here must be non-negative. But this thing here being non-negative is just a very well-known inequality for convex functions, right? The difference minus the function values minus the gradient times the difference in x's is non-negative. So this is a standard inequality for differentiable convex functions. Okay, so you can just use the definition of the hyperconvex functions using these two definitions of convexities, and you can prove that this is a necessary condition, but you know, we just have to check it for all the data points, and then we know the data points can be interpolated by something from this class. Okay, and the nice thing is the proof is constructive. So basically, if you give me the data set and it can be interpolated, I can construct a function that does interpolate it. It's also important for us.
Etienne,
Yes?
does it matter whether L is positive or not?
Yeah, L is positive, always. Or non-negative, to be precise. Yeah.
But mu can be negative.
Mu can be negative for now, yeah. Yeah, so indeed, it's, yeah, no, indeed, it's not shown in the nested loop, that's right. So it's not clear here, but L should be non-negative.
Positive.
It can be 0.
Because L is you divide by L. So.
Okay, I divide by L, then that's positive. Okay, so just to list the historical development. So basically, these were the two papers from 2017 by the Leveux-Leneuve group, and it has just been updated. So they first did the case where L is finite and mu is strictly positive. These are called the smooth, strongly convex functions, of course. Then it was extended also to the L smooth functions. So you know that then that case mu is minus L, and then of course, and now the general case where mu can be negative but not necessarily equal to minus L. This is the most general hyperconvex case, and it was only settled this year. So there's a nice development here, and then the thing I showed you is really is a theorem from this year. Okay, so, and then finally we end up with something which is, I claim to be tractable. So we still have our choices of objectives from before, and now we have no longer variables that are functions from this function class, but just some vectors. So we will now have variables which correspond to points, unknown points, xk generated by Cauchy's algorithm. The gk is corresponding to the gradients at those points, and the fk is corresponding to the function values at those points generated by the Cauchy method. Okay, so let's say we want to minimize the distance from optimality in the function value, so we choose this objective. The worst case is where this is a maximum, so that the function value after n iterations minus the optimal value is as large as possible, so that's the worst case function. The function has to be from this class of hyperconvex functions, and that is modeled by these inequalities here. And remember again, so this is tight. So whenever we will have a solution to these inequalities, then we will be able to construct a hyperconvex function that matches these constraints.
So F star or X star assumed to be known?
No. No. We don't. We can fix it without loss of generality. Yeah, but I mean, yeah. So that's the right answer. You can fix it without loss of generality, even to 0. Yeah. So, but I mean, this is just for the exposition. So then basically, what else do we have? We have that using the method of Cauchy, the new point is the old point updated by the step length tk in the minus gradient direction, and we can also add this inequality from the descent lemma. It cannot hurt, so it might help us. And then we had the starting condition that just bounds everything nicely. So the starting function value is bounded from the optimal function value by this given parameter delta. And the gradient at the optimal solution is of course a 0 vector. Yes, so now we have variables again, these xk's, fk's, and gk's. And the parameters are as before. The parameters for the hyperconvex functions are delta, the number of steps, and the step lengths. And the whole point of this is now this problem is tractable. This is a so-called semi-definite programming problem, and it can be solved to any fixed accuracy in polynomial time. So if you want to solve this problem numerically, you can do so, provided that this is small enough to fit in your computer. And the size of this program is determined only by the number of steps that you take, this capital N. So why is this a semi-definite program? It's because these unknown vectors only appear in inner products. So for example, here we have these unknown gi's, gj's, and xj's and xi's. but they appear in inner products. So instead of treating them as the variables, we can just treat the inner products as variables. And these, so we can just say these inner products are the entries of an unknown gram matrix. Okay, so that's why this is in fact a convex optimization problem in disguise. We can just replace these inner products by entries of an unknown gram matrix. And the very nice thing about that is we no longer see the inner product then, and we also no longer see the number of variables. So we don't see the dimension of the problem anywhere. And finally, this solution of this optimization problem will exactly give us the worst case performance, provided that the number of variables is large enough. In particular, so this n determines the size of this problem. And as long as the number of variables is large enough, then we will have an exact correspondence. So this is a precise reformulation of the worst case performance of the Cauchy method for hyperconvex functions, and with the property that it's exact and tractable.
Can you remind me for the equation with the xk plus 1 equals xk?
Yeah, this is just the Cauchy method.
No, I understand. But as yeah, right. Just in terms of representing it as the STP.
Oh, we will eliminate the x variables. So we can just eliminate all these variables. Okay, so yeah, that's a good point. So I said everything appears in a product, so that has to be true. We get rid of this by just using these equations to eliminate the x variables. Yeah, true. Okay, so what can one then get as results for the worst case performance of the method of Cauchy for these functions? So we start with a case where mu is positive, so we have a strongly convex function, and L is finite, so we have L smooth strongly convex functions in this case. So what we could show in 2017 is you can then solve this semi-definite program in closed form, not just numerically, but you can get the closed form solution. And then you find that after n iterations, provided that you use the step length 2 divided by mu plus L at every step, so you just use one step length, this one, then after n iterations, then the function value, distance from optimality, is the old distance at the start reduced by this factor here. So basically, at every iteration, you get a reduction by L minus mu divided by L plus mu, which is smaller than 1, squared. So this constant here determines the so-called linear rate of convergence. So the linear rate of convergence of the method of Cauchy was known already for strong L-smooth strongly convex functions, but this constant was not known in general. So we just basically fixed this constant. Okay, so in particular, this exact result was known earlier, but not for the whole class, but just for quadratic functions, which belong to this class of hyperconvex functions, which are strongly convex, and it's also tight. So the interesting thing is also this exact same result with exact same error bound holds if we do not use this fixed step length, but we select the steps through exact line search. Then we also get exactly the same rate of convergence. And this was shown in this paper. And what is this quadratic example? Or what is the example that shows that it's tight? So it's a simple example shown here. So it's actually a family of examples for any n. And what we do is we just, it's just basically a homogeneous quadratic function with a diagonal coefficient matrix. So the lambda 1 is just the mu for our function class. The last lambda is just the L for our function class. And the other lambdas are in between. The values do not matter. So we start at the point where only the first and last coordinates are non-zero. And then basically throughout the algorithm of Cauchy, we will stay in the same plane where these intermediate coordinates are 0. So it all reduces to a 2-dimensional problem, which is indicated in this drawing. So these are the steps of the Cauchy method. And the interesting thing here is the step lengths are indeed as indicated. So the step lengths here are precisely those step lengths, but they also happen to be exact line search step lengths for this example. And you can just see this graphically because the step takes us to a point which is tangent to the contour. So here again, it's tangent to the contour. For this example shows, establishes the worst case behavior for both fixed step length of the shown size and the exact line search. And the other side is shown by the semi-definite programming bound. Okay, so that is the strongly convex L smooth case. And now just to say, how do we find this closed form solution of the semi-definite program? So it's clear how you would do it numerically, but how do you do it analytically? And the answer is this is more of an art than a science. So basically what we do is, we aggregate the constraints in the semi-definite program by just finding the optimal Lagrange multipliers of a dual. So basically we find the optimal Lagrange multipliers, which are the optimal solutions, optimal variables in the semi-definite programming dual problem. And how do we find these multipliers? Well, we solve the SDP numerically for many choices of the parameters. So we are just getting some data, and then we know that these optimal multipliers, they have to be algebraic functions of these parameters. So we just do some reverse engineering and try to guess the answer. And then finally we guess the answer, and then we just verify the correctness through symbolic calculations. So so I wish I had a simpler answer. I often get asked, how do you find these complicated expressions? Well, there is no simple answer. You just keep trying. Sometimes you're lucky and you find the closed form solution, and sometimes you cannot. Okay, so then the next thing that I would like to talk about, which is for me very interesting, is that this function class f mu L depends on the reference inner product. So why? Because it's defined in terms of a norm. So if we have an underlying reference inner product, of course that induces a norm. And so let's just try to understand what happens. So first of all, we have to understand that the gradient of a function depends in some sense on the underlying inner product on the space that we use. So in terms of Fréchet derivatives, the gradient at x is a unique vector g of x that satisfies this limit equation. Okay, this is just the standard definition of a Fréchet derivative. But what is unique here about this derivative? So basically, this linear operator here is unique in the sense that if you view this as a linear operator acting on h, so this is a linear function of h, this is the unique part. But so if we would change the inner product, the gx part will have to change to make it invariant. So this is an important thing to understand. And so basically, if we had a Euclidean inner product, then the gradient we get is just the vector of partial derivatives. So this is what the students learn in calculus. But I mean, this is a limited view because this is really for the standard inner product. So basically, there are infinitely many inner products, of course, on Rn, but they all arise through linear positive definite self-adjoint linear operators, self-adjoint with respect to the underlying inner product. So if we can define a new inner product in terms of the reference one, and we note this by the operator, so then we just do this instead of using the identity there, and then we get a new inner product. And all inner products arise in this way on Rn. So why is this interesting or useful? Well, the idea is that, how does the gradient change? So if we change the inner product up here to the B inner product, and it's easy to see we will have to change the gradient to B inverse G to make this thing invariant. And so if we change the inner product to the B inner product, then the gradient changes to B inverse times G. So basically we can, instead of just analyzing the steepest descent gradient of partial derivatives, we can analyze steps using anything of this type for a positive definite operator B. Okay, so why is this interesting? So it's interesting because then we can analyze Newton's method in this way, not just the Cauchy method. So if a function is twice continuously differentiable, then it has a Hessian. So and then this self-adjoint Hessian, and this Hessian satisfies again this equation for the Fréchet derivative. And then basically then the idea is that we can now fix one point in the domain of a function, and we define as a positive definite operator, we take the Hessian at that fixed point. And what happens then is that the gradient changes to this operator, which was B inverse before, but our special choice of B is this Hessian at the fixed point. And if you look at this thing, this is precisely the Newton direction, but with a minus sign. Okay, so we can obtain the Newton direction as a special case of the gradient by just changing the inner product. And so we can analyze one step of Newton's method by using a suitable inner product. Why only one step? It's because, you know, if this Hessian will change with x, so we're just fixing x. So if we just look at what happens at the fixed x, we can analyze a step of Newton's method. So basically, the interesting question to answer still is then what class of functions, what happens to our function class f mu l? What happens to our class of hypoconvex functions if we play this game with the inner products, and what are these values of mu and l? So I mean, so how do we interpret these results that we just obtained for Cauchy's method for this function class? So the thing to remember, which I already mentioned, is a function belongs to this function class if and only if the spectrum of its Hessian is basically contained in this interval between mu and l. And up to now, I only spoke of all of Rn, but you can also limit this to some domain, and then this is you can consider this definition of the function class with this more general definition. So, okay, wait. Whoa. Sorry, I went to wrong thing. Yeah. Yeah. Okay, so the first thing we have to understand is, you know, since the gradient changes with the inner products, and so does the Hessian. So basically, if we change the inner product from the standard one to the one defined by the Hessian at the fixed point, then the Hessian at the point y just becomes this operator here, which is just denoted usually by hxy. So the subscript x just reminds us that we have to multiply it by this linear operator from the left. And the idea is now that our function class f mu l corresponds to a known class of functions which are called self-concordant functions. And just to make this believable to you is just to tell you what is the definition of these self-concordant functions. So basically, the self-concordant function is called self-concordant if for any point in its domain and any point y in a ball around it, the ball defined by this inner product of ours, defined by the Hessian at x. So then this must still be inside the domain, and the spectrum of this Hessian must be contained in this interval. Okay, so the spectrum being contained in the interval is exactly what we're talking about. So we're going to associate this mu with this value and this L with this value. Okay, so I am going slightly slow, so I'm just going to jump to the conclusion of this. So basically, the worst case analysis of the gradient descent method applies here. We just have to reinterpret our function class and our inner product, and then we can analyze one iteration of Newton's method. And the function class that we can analyze is a class of self-concordant functions. So if you want to read more about this, this is some work we did published in 2020, and it's useful because Newton's method for self-concordant functions is used in the complexity analysis of interior point methods. So this is we could get some new insights by applying this procedure to these self-concordant functions, to Newton's method for these self-concordant functions. Okay, so just then I'm just going to speak to you to just a few more results, just quickly. So L-smooth functions were also special cases of hypoconvex functions. And then just something that I did recently with my postdoc and Muslim Zamani and PhD student Hadi Abazadeh Payfasti was to show that in this case we can look at the different objective criterion. So if you remember, one of our criteria was we tried to minimize the gradient norm, but in this case we're talking about just L-smooth functions. So these need not be convex. So in this case, you know, trying to find a convergent sequence of these norms is unattainable. So I think Amir Ali will tell a bit more about the complexity of finding stationary points later. So the best thing one can hope for is to say something about this objective, which is to say that we have a lot of iterates, xk, and then at least the smallest norm of the gradient taken over all the iterates will be no larger than a given value. And this value goes to 0 as 1 over the number of iterations, which is big N. Okay, so again, this basically the sublinear rate of convergence was known before. This basically that this is order 1 divided by capital N, but we again established the exact constant. So this constant is exact. And so how you know that it is exact is, again, we can just construct an L smooth function that matches this bound exactly. And in this case, I don't give the details. I just give a picture that corresponds to specific values. So in this case, L is 1, the delta is 2, the number of steps is 4. And these are the points 1, 2, 3, 4 that we generate during the algorithm. All the step sizes here are 1 divided by L. Sorry, I should have said this. This result is for fixed step sizes, or at least the result that I'm showing. And so indeed, for this example, we get exactly the same bound as in the theorem. So again, we can get the tight convergence rate for L smooth functions for the special case where the step length is 1 over L. Okay, so I want to skip this part. I'm just going to say that we can keep playing with this function class. We can keep adding new features to it that help us to derive new results. But I mean, this is something that you can read more if you wish. So just there is something called the Polyak-Łobaszewicz inequality. And if you are interested in reading how this helps us to prove a better convergence rate, you can just look at this recent work with Samani and Abbas-Sadegh-Paifasti. So the only thing I want to mention is this condition, which is called the PL inequality, is weaker than convexity, but it still helps us to prove something faster than a sublinear convergence rate. So if you just glance at this error bound here, this constant here is something smaller than 1, so it defines a linear convergence rate. And so this is something better than you can get just for L smooth functions, for example. So this is not convex, but it still allows us to get some linear rate of convergence. And it's the weakest condition one can impose instead of convexity and still get this linear rate of convergence. Okay, so then I just would like to wrap up by just saying that, you know, this very recent paper by Glenier and Rotaro and Patrinos, they have more tight results for the gradient method for hyperconvex functions. I didn't cover all the cases. And of course, I to keep things a little bit understandable, I only talked about the method of Cauchy. So you can also analyze other methods like ADMM, the convex concave procedure, or DCA. You can do accelerated gradient methods. You can study stochastic gradient methods, operator splitting methods. So there's a whole literature about this already that I cannot cover. One thing I would like to say is there is a very useful piece of MATLAB software due to these authors, again, Taylor, Hendricks, and Glenier. And this software does the numerical calculation of these worst case convergence rates by solving these semi-different programs that I've shown to you. So this is actually extremely useful piece of software. I use it to teach my graduate students. I think some students here have actually used it to do some assignments. And then if you want to learn more on an introductory level about this topic of performance estimation using semi-different programming, the PhD theses of Yoel Drori and Adrian Taylor are both online, and these are really excellent pieces of work that introduce the topic. So then finally, I would like to say congratulations to Monique. I do not have a picture of when Monique was awarded the CWI fellowship, but fortunately Monique has many fellowships, including the Royal Dutch Academy of Sciences, or KNAW in Dutch. And this was taken on the occasion when she received the KNAW fellowship. So Monique, heartfelt congratulations, and may there be many more. Okay, that's it. Thank you.
Does this work? Yes. Yeah. So Etienne, thanks a lot for this beautiful talk, and thanks also. I mean, it was perfect on time, so it was a fantastic talk. I think very nice. So actually, I forgot to mention, like, if you have questions, then it would be actually nice if you could, raise your hand, and there is a mobile microphone that walks around and kind of will give you the microphone. So we have actually time for some questions. Please go ahead. Let us know if you have any questions to Etienne.
Hello, thanks. Etienne, wonderful. I have two questions, actually, if you allow me to ask them. So the first one would be, immediately from the start, you started defining your classes of functions with respect to the L2 norm. But there's also a lot of work on L-smooth functions with Bregman distances. I guess you can accommodate this as well by just playing with the norms, right?
I think we discussed this in the past. So, I mean, the thing is just that if these are induced norms, yes. Well, I mean, so but you see, if you use more general metrics than induced norms, then your interpolation theorems don't work anymore.
Okay.
So the interpolation theorems are independent of the inner product as long as you interpret the gradient correctly.
Right.
But if you go to other metrics that are not induced norms, then I don't think things carry through.
So for these functions, your technique would not apply at the moment?
No, because you don't have these interpolation theorems.
Interesting.
Yeah.
Okay. And second question, more out of curiosity. So the last result on the Pierre-Yoshiev inequality, can you quantify the mu p? Can you compute it somehow? Because this is usually the hard part, right?
Yes, no, I mean, I think these things, you can ask the same of this mu and L for the hyperconvex functions. I think these are theoretical studies. In practice, calculating these constants are harder than the problem that you are interested in. So you restrict yourself to the class, and that's it.
Okay. Thanks.
Yeah, thank you. So, any other questions from the audience?
I had a question on the interpolation theorem. You said you can restrict it to a domain that isn't the whole thing, but is it the same theorem?
No, indeed. So I skipped the details. It's a very good question. So you have to be more careful. You only have weaker conditions. So it's not. You cannot simply get the same interpolation condition when you restrict to a smaller domain than all of Rn. You have to adapt it slightly. But I just swept this under the carpet.
There is some result.
Yeah. There is a result. So this paper I mentioned in connection to the Newton method develops this theory.
Yeah, there's another question here.
Does your class of functions exclude multiple local minima?
No. Well, I mean, L-smooth functions can have multiple local minima. So, yeah. In the most general case, no, it doesn't exclude it. But I mean, of course, if you go to positive mu for strongly convex functions, of course, that's a unique global minimum then.
Any other question? I don't see. No, I don't see another question. So then, let me thank you very much for this very nice talk. And actually, there is we have some nice cadeautjes. So wait a second. Nice chocolate inside here, and a very special limited edition of CWI Lectures. Thank you very much for bringing us. Okay, so that brings us to our second invited speaker of the first session. So it's Frank Valentin. So Frank is a full professor of applied mathematics at the University of Cologne since 2013. And he's actually well-known in our group and at CWI. So Frank was actually a postdoc and a researcher in the Algorithms, Combinatorics and Optimization group. It's the former N&O group here at CWI from 2005 to 2009. He then moved on and was an assistant professor at Delft University of Technology from 2009 to 2011. And then in 2012, he was promoted to associate professor at Delft. And in 2013, then moved back to Germany, where he since then is a full professor. So Frank has a very broad interest in actually combinatorial optimization in discrete geometry and in combinatorics. He's an expert in semi-definite programming, in harmonic analysis, in geometry of numbers, as we'll also see, coding and information theory. So he actually is an associate editor of various prestigious journals, among which the Mathematical Programming Series A journal and Numerical Algebra, Control and Optimization. Frank also received various prestigious grants and awards, among which the prestigious VD grant by the Dutch Research Council. He's one of the co-PIs of the Marie Curie International Training Network, MINOA. He has received various DFG grants, like from the German Research Foundation. And in 2011, he received the SIME Activity Group on Optimization Prize, as an additional award. So Frank will speak about an intriguing number that actually connects semi-definite programming, and the title of his talk is Generalizations and Applications of the Lovász theta number. Frank, it's a great pleasure to have you. Please go ahead.
Good. So in this talk, I want to talk about the Lovász theta number. And yeah, so as Guido mentioned, I was a postdoc here between 2005 and 2009. And then in our discussions with Monique and with Lex, then the Lovász theta number came up quite often. It was either the beginning of a discussion or it was the end of a discussion. And for this reason, I think it's appropriate to talk about this here. And it made a lasting impact on me, these kind of discussions. Good. So the Lovász theta number. So this is Lovász, and the Lovász theta number was defined in this paper, the Shannon capacity of a graph from '79. And this is really one of the founding papers of semi-definite programming. And yeah, what's inside? Yeah, many nice things, but I mean, first of all, it's going to be a graph parameter, which has to do with combinatorial optimization, and therefore I will introduce it kind of slowly. So combinatorial optimization is usually optimization over a graph. So this is all the beginning of it. And we are interested in finding independent sets of large size. So an independent set is a subset of the vertices, so that no two pairs of vertices are connected by an edge, like these four, like these. Now I understand. Wow. So like these four red points, they are not connected by net, they're independent. Another question is find an independent set which is as large as possible. Yeah, and it turns out that here in this setting, 4 is the optimal choice. You cannot find 5 vertices which are not connected by edges. And therefore, we say that the independence number, also called alpha of G, is equal to 4. Yeah, so that's an important graph parameter. And yeah, from a computational complexity point of view, then it's easy to see that finding the independence number is an NP-hard problem. So you cannot expect to find an efficient algorithm which solves this problem for arbitrary graphs. But on the other hand, and now Lovász theta number comes in, is that the Lovász theta number gives a bound for alpha, an upper bound for alpha, which you can compute efficiently, which you can compute in polynomial time, and which you also can compute kind of on, not only in theory, but also in practice. Okay, so how does this work? So let's introduce the theta number. So what we do is, in the step 1, we go from the graph to analytic geometry. So we go from graphs to linear algebra. So here in this example, I show you a graph on 5 vertices. The vertices are indexed between 0, 1, 2, 3, 4. And we have edges between 0, 1, 1, 2, 2, 3, 3, 4, and 4, 0. Okay, so that's the combinatorial data. And from this combinatorial data, we use some analytic geometry. So what we are going to do is we look at the characteristic vector of an independent set, chi I. So for example, in this case, I look at the characteristic vector of 1, 3. So that's an independent set, these two vertices. And this is this one here, this vector, which has 5 components. For every component, it is either 0 or 1, and every component corresponds to one of the vertices. And I put a 0 if the corresponding vertex, that's vertex 0, this is not belonging to the independent set. And I put a 1 if it belongs to the independent set. Yeah? So here I put a 1 here because the number 1 lies in the independent set, and here I put a 1 because the number 3 lies in the independent set. All the others are 0. Okay, yeah, why not? Okay. Then I do something maybe strange at the beginning. I take the outer product. So I take the outer product of this characteristic vector, looking at it as a column vector, times the row vector, giving me a matrix where the row and columns are in the vertices of the graph, and I have 0 and 1s here in between. So it's a rank 1 matrix, which has a couple of nice properties. Yeah, so what are the nice properties of it? Yeah, first of all, this matrix is symmetric and positive semi-definite. So we will later optimize over these kind of matrices. So positive semi-definiteness is important. Then you see that you have at the entry ij is 0 whenever you have an edge between I and j. Because here I look at independent sets. I take the outer product of the independent set vectors, and in the independent sets, I cannot have an edge between I and j. Next nice property is that if I sum up all the entries of this matrix, I get a 4. Yeah, 4 times the 1. And that's exactly the number of points in the independent set times squared. Yeah, I mean, this also works, of course, for other characteristic vectors. Next thing which we can do is we look at the trace of the matrix, so the sum of the diagonal entries. And then we see that the sum of the diagonal entries is equal to 2, 1 plus 1, which is also, in the general case, a number of vertices in an independent set. Okay, and these 4 observations, we will just use them now, and we will forget about that this A was coming from an independent set. We are just using these 4 observations to come up with a formulation of the zeta number which upper bounds the independence number. Yeah, so we go from analytic geometry to convex optimization to semi-definite programming. So we just kind of saw that alpha is upper bound by theta, and then theta of g, the lower theta number, is this maximization problem, where you just use the observations I had before without really assuming that A came from the construction characteristic vector of the independent set times characteristic vector of the independent set transpose. And because we don't require to have that this A was coming from this construction, we have an upper bound for alpha. Yeah, and that's the theta number of lowers. Okay, and now we are in the business of optimization, in the business of convex optimization. So we can apply duality theory to turn this maximization problem into a minimization problem. Yeah, that's also something we are usually doing if we do convex optimization, that we can play with a primal dual. Okay, so this number was introduced by Lobas, 79, to compute the Shannon capacity of the 5 cycle. He also looked at the primal dual pair there. Then, a few years later, Grötsche, Lobas-Schreiber in 81 showed that one can indeed compute theta efficiently, polynomial time, using the ellipsoid method. I guess in the 80s, this was probably like science fiction, that you really can compute things in polynomial time, because the ellipsoid method we know is not so really fast. But then over the last years, yeah, things became really effective, especially because interior point methods came about. And now it's really possible to compute the theta number of a medium-sized graph, a couple of thousand vertices on a laptop. So this is really working. And one good thing about this primal dual situation is that if you want to find an upper bound for alpha, we only have to find some feasible solution for the dual. Yeah? So in order to find an upper bound for alpha, we somehow, for example, by computer, by guessing, or by some other means, we have to give a feasible solution for the dual, and then this gives us an upper bound for alpha. Yeah? It gives us a proof strategy to find good bounds for alpha. Yeah, so we have to find an M, we have to find a matrix B. so that these things are fulfilled. And once they are fulfilled, I have a bound for alpha. All right. Good. So now we add some algebra to the picture. So we do some symmetry reduction to simplify the computation. Yeah, so in this 5-cycle picture, things become very easy. But there are kind of an example case for the things which come later. So let's try to understand them. Okay, so you have this 5-cycle. You want to compute the theta number of. And then you see that this 5-cycle, you can turn by 72 degrees, and you stay on this 5-cycle. So you can do a cyclic permutation of the vertices. Yeah, so you can move 0 to 1, 1 to 2, and so on. And this is done using this cyclic permutation matrix. Okay, and then the trick is that if you have a feasible solution B for the dual, which can be written like this. Yeah, so matrix B, where on the diagonal you have m's, and then you have some other values which you have to specify. Then you apply this cyclic permutation from left and right, so you conjugate by this permutation matrix. You get another matrix, C transpose BC, and it has the same structure because the cyclic permutation matrix maps the graph to itself. And if you have a feasible solution for the dual, also after doing the cyclic permutation, you also have a feasible solution of the dual. You have the same zero pattern, the eigenvalues stay, the objective value stays. Okay, that's nice. And now you can do it not only once, you can do it a couple of times and do sum over the entire cyclic group. Then you get, after doing this, you get this matrix here, which when B was feasible for the dual, it's also feasible. But now something kind of nice happens. It happens that the optimization problem does not depend on 6 variables as here. It only depends on 2 variables because you can aggregate this B0i's or Bij's into 1B. Yeah, so that's one nice thing which happens. And another nice thing which happens is that if we look at this matrix here, this matrix has some extra structure. It has, I mean, once you understand the first row, you also understand the other rows because the other rows are just shifted by 1 to the right, and then you're coming back. So you have a circulant matrix. And yeah, many things are known about circulant matrices. For example, you can understand the eigenvalues by taking the discrete Fourier transform. And eigenvalues are important because we want to see that this matrix is positive semi-definite. Yeah, and then we can restrict our optimization from arbitrary matrices to circulant matrices, and then things become much easier. Okay, things become much easier, and we are saying this by taking the appropriate Fourier basis. Yeah, circulant matrices are connected to the discrete Fourier transform, and now you can play this game not only for finite groups, but you can also play it for more complicated groups, and things still work out. Yeah, so, for example, you can consider graphs on locally compact abelian groups, finite, and you can play the same game. Then you can encode the first row of your circulant matrix by some vector, or in the setting of more complicated groups by functions lying in L1 of A. So this F specifies the first row of the matrix. Then you can encode that this matrix is positive semi-definite by the fact that the Fourier transform of F corresponding to the group is non-negative everywhere. And then technically you see that the theta number you want to compute is this minimization problem over here. Yeah, so you minimize F0 so that F lies in L1, that's the optimization variable. You want to have that these Fourier coefficients are non-negative, and you want to have that f of x is equal to 0 when you have an edge between 0 and x. And f hat is a corresponding Fourier transform of your abelian group A.
Why minimize F0? Where did that come from again?
So if you recall, I didn't really say that, of course. If you recall this structure here, then F0 corresponds to these diagonal elements here. And these diagonal elements, if you recall, that's many things to recall, of course, then this M corresponds to minimizing M on the dual side.
And did we encode the B minus J? Like, I guess that's the all ones vector or something, right?
Exactly. So I didn't say that. So the J matrix is the all ones matrix. And then I want to have that B minus this all ones matrix is positive semi-definite. And this is encoded by saying that f hat of 0 is greater or equal to 1.
Okay. Yes.
Okay.
If you say, consider set V as elements of an abelian group, do you mean consider V as A?
Yes, V is equal to A.
Okay, so the elements of the set are elements of.
Yeah, so V should be V equal to A. And A in this example we had before was Z mod 5Z. And you can also do it for more complicated abelian groups, Rn for example. And then this is also working out. Yeah, so this generalizes a lot the Lovász-Titon number of the original paper, because there it was only about finite graphs, but here it also works for locally compact abelian groups. And this has many nice applications. We come to that in a minute. Yes, exactly. Yeah, so you have edges. You say what the edges are between 0 and you specify the neighborhood of 0, and then you move this neighborhood to all other points. So you need also symmetry on the edges. Yeah, so I see the audience is listening. Very good. All right. Okay, but why do we care? Why do we care about alpha and theta? Yeah, short answer, alpha can be used, the independence number can be used to model packing problems. So where the vertex set corresponds to all possible positions of the objects you want to pack. And you have edges between pairs of objects which overlap. And then an independent set in the setting corresponds exactly to a valid packing. And then finding a packing which is as large as possible, by density, for example, is an interesting problem. Yeah, one application is, for example, the situation of error-correcting codes. So when you want to communicate over a noisy channel, then you want to find a good packing of code words. For example, good packing of Hamming spheres in the binary code case, 0, 1 to the n. The continuous setting if you want to do a sphere packing in Rn. Yeah, so this was already realized by Shannon that communicating over a noisy channel can be done best using sphere packings in some space, especially in high dimensions. What you also can do is you can look at really concrete packing problems in like dimension 3, where you, for example, want to pack geometric shapes like these ellipsoids here, or I think these are M&Ms. And you want to pack as densely as possible these M&Ms in some container. Yeah, so this is another application. And yeah, as I said, I mean, finding alpha, finding the optimal solution is a hard problem. But using theta, you can find interesting bounds for it. And this has been done in a couple of cases. Yeah, first of all, Lovász also used it in an error-correcting code setting, where he computed the Shannon capacity of the 5 cycle, which is square root of 5, answering a question of Shannon. Then you can look at it also for packing on unit ball. So you can solve the Kissing number problem in dimension 8 and 24 with it. So what is the Kissing number problem? So you have a unit sphere, which is in the middle, and you want to attach other unit spheres to it so that things don't overlap. And then you want to maximize the number of points. You want to maximize the number of spheres around it. So it's a local sphere packing problem. And then Odlyzko, Sloan, and Levenstein, independently in 1979, could find the solution of the Kissing number problem using this framework. They were talking about the framework of the Del-Zart bound, but in this setting, they coincide. And then more success stories, so encoding theory in the framework also of the Del-Zart linear programming bound. These 4 Americans, McAllis, Rodemich, Rumsey, and Welsh, 1977, Kabatiansky, Levenstein could prove asymptotic bounds for error-correcting codes in the binary setting and here on the sphere packing setting. Yeah, so these are kind of the success stories from the 70s. There are more success stories, more recent. Then in 2003, Kohn and Elkis could find a numerical solution using this theta number of the sphere packing problem in dimension 8 and 24. So they could extend the Kissing number problem to, or they could almost extend the Kissing number problem from the local version to the global version. So they could find good numerical solutions, so which were very close to the optimal solutions. Then together with David Delat, Fernando Oliveira, we could adapt this Kohn-Elkis bound or the lower theta number for packings of spheres of several radii, like here. Like here. Then together with Maria Dostad, Cristobal Guzman, who also was a postdoc here, I think, Fernando Oliveira, we could also use this technique to find new upper bounds for translative tetrahedral packings. So we could go from spheres to non-spherical shapes like tetrahedra. Yeah, and then recent breakthroughs by Marina Wiazowska. She could use this framework to find the exact solution for the sphere packing problem in dimension 8. So she could find the optimal solution of the theta number. And this is very, very tricky because next to algebra geometry, she also had to introduce some number theory to the picture, and she had to introduce some modular forms to find the optimal solution for the theta number. And then 1 week later, after Marina's breakthrough, Henry Coe, Abhinav Kumar, Stephen Miller, Danilo Radchenko, and Marina, they could find the exact solution of the sphere packing problem in dimension 24. Again, using modular forms to construct the optimal solution for the number for the corresponding problem here. Good. Yeah, but sometimes, I mean, these are success stories, but sometimes theta is not good enough. Yeah, sometimes we have the case that alpha is really too far from theta. So what do we do then? Yeah, then we try to strengthen the lower theta number. And kind of the beginning of the story is, there are these 2 papers by Joe Bernal-Lasserre and Lex Schreiber from 2002 and from 2005. And yeah, when I was a postdoc here, I mean, these 2 papers were the hot stuff, I would say. We're really interested in it. But these 2 papers are really hard to understand. Sorry. so Jean's paper is hard to understand because it involves difficult real algebraic geometry. It involves the Putinas Positivstellensatz. And Lex paper is difficult to understand because it involves sums of product of 4 times binomial coefficients, which is also difficult to digest. Okay, but luckily there were 2 papers by Monique. One's on bounds for codes and one's for comparing different kinds of hierarchies for 0-1 programming, and they helped me a lot to see what's really going on. So let's see if I really understood them. Okay, so here is what I think is Monique's explanation of the Lasserre hierarchy. Okay, so we start out with a graph. So I should take the 5 cycle again, but this is too complicated because the matrices would become too big. Okay, so now we take an easy graph, 0, 1, 2. And instead of using the characteristic vector just on the vertex set of the graph, we take the characteristic vector on the power set. Yeah, so we take characteristic vector of I of the power set, R to the 2v. So we have to say for every subset of the vertices j, we have to say what the entry of chi has to be. And here we say it is 1 if j is contained in I and 0 otherwise. Okay, so here's the example. So here my independent set is 0, 2, this vertex and this vertex. And then I take chi, again, outer power chi times chi I transpose, do this construction, and then I get this matrix here. It's again a rank 1 matrix. But where now rows and columns are indexed by all the subsets of the vertices of the graph. And I have a 0, 1 structure corresponding to this containment relation. Okay, so it's a very big matrix, exponential size in V. But okay, so let's do some observations. So first of all, A is symmetric, positive semi-definite. Then I have zeros whenever I have a 0 at position j, j prime, whenever j union j prime is not independent, which generalizes the case which we had before. There we had just 2 vertices, and they are connected by an edge, meaning they're not independent. But here, things can become more complicated, so we're just saying that they're not independent. Next important thing is that the A empty set is equal to 1, this part here, because the empty set is always contained in any other set. Then if we sum over all vertices, so we just take not the entire power set, but we just take the singletons, then we see that we have the number of elements in the independent set. So in this case, I have to take this one here and this one there, sum it up, and I get 2. Then also interesting, A has moment structure, which means that the entry A, J, J prime only depends on the union, J, J, union J prime. And also important, A has natural submatrices, and they're indexed by subsets of fixed cardinality. And here I indicate them by these red lines. Yeah? So this is the first submatrix, only indexed by the empty set. Here is the second submatrix, only indexed by sets up to cardinality 1, here sets up to cardinality 2, and here sets up to cardinality 3. Yeah, and this kind of matrices, they help us to strengthen the theta number. Okay, and we can use them to define the t-step of Lasserre's hierarchy. So what we are going to do is we look at all subsets of V of size at most t. So this corresponds to looking at specific submatrices. And then we collect simply the observations we are just having. Yeah, so we maximize the sum of the singletons AII. A is positive semi-definite, has moment structure. A empty set is equal to 1, and we have equal to 0 whenever J union J prime is not independent. Yeah, so this gives us a sequence of growing semi-definite programming problems. And Monique showed that the very first step of Lasserre's hierarchy is simply the theta number. then these numbers can grow. And at the end, at the alpha step, they converge to alpha. Yeah, so in principle, you can use this Lasserre hierarchy to determine alpha at the end. Is the other way around? Oh, yes. Okay, thanks. It's the other way around. Very good. Oh, sorry, yeah. So it's the other way around. Sure. Okay, so that was one part of Monique's paper, but it was correct in Monique's paper. Then Monique showed that the bound by legs lies between Lasserre 1 and Lasserre 2. So it's strengthening the theta number, but it is not quite Lasserre 2. And she proved that for fixed t and for binary codes of length n, one can compute the t-step of Lasserre's hierarchy in polynomial time in n time.
But you say schijnbaar is loopbaar. Is loopbaar, hè? The theta.
This is Lova's bound, but your bound from the previous paper lies between Lasserre 1 and Lasserre 2. Yeah. Okay. Okay, and then we were building on Monique's synthesis. So with David Elard, we were able to generalize Monique's view to infinite geometric packing graphs. And this provides the framework of 2T bounds. Then using this, we could find also new upper bounds for kissing numbers, 2008, together with Christine Machoc. Then we could use it to prove the optimality of a 10-point configuration on S3. So we could find a configuration of 10 points on S3, which are at largest distance, and we could prove that what the largest distance is. Then Kohn and Wu used this framework to look at universal optimal solution of 7 points on the projective plane. Yeah, so they go from packing problems to energy minimization problem, and then they have framework of universal optimality, which means that these points minimize energy for arbitrary, completely monotonic potential functions. Then David was able to solve energy minimization problems completely with 5 points on S2 numerically, Lasserre 2. Yeah, then we could squeeze things a little bit, and we were computing 6-point bounds for equiangular lines, together with David, Fabrizio Machado, and Fernando Oliveira. Then Maria Dosta, David Elard, Philippe Moustrou could prove the optimality of 183 points on the hemisphere of F7. So they were taking S7, the upper part, and they were able to find out what is the optimal distribution of 183 points. They are, of course, connected to dimension 8 and the corresponding structures which optimize packings. And then recently, David, together with Henry Cohn and Andrew Salmon, they were able to compute new upper bounds for sphere packings using the 3-point bounds. So using something which lies between Lasserre 1 and Lasserre 2. So for example, if you want to find the best known sphere packing bounds in dimension 4, it's in their paper. And behind the scenes of basically all these results, you find some numerical, kind of challenging, difficult computations, solving difficult semi-definite programs, which then afterwards are made rigorously using some post-processing. Yeah, so here there's first of numerical results, but then they are turned into rigorous mathematics by using some post-processing. Okay, So this was building on Monique's and Lasserre's and Lek's papers. The story continues, but not today because things are becoming too technical and too long. So together with Davi and Fernando and Lucas, we were able to generalize the lower theta number for graphs to hypergraphs. So we could also define an independent number for hypergraphs. We could define a theta number which upper bounds alpha, and we could do some, also asymptotic estimates to look at it. And here are these two papers. So the theta number is really a continuous story of kind of my scientific work the last 15 years, which was starting kind of here with Monique and with Lex. And so this had really a strong and lasting influence on me. To end the entire story, I also asked around the other postdocs Monique had. So Monique had many, many postdocs, I realized. It was also difficult to find a complete list. And I'm not sure if I have a complete list now, but we are getting close to it. And when everybody sent me some input and said basically the same thing, which is here, so giving the voice to some of Monique's former postdocs. And everybody agrees that Monique is doing a very good job as a postdoc supervisor. It's very hard to read, but I knew that, so I give it to you. Please. Thanks for listening.
Yes, thank you very much for the beautiful presentation, and especially also the final course. I think it's very intriguing. Everything. I mean, the theta number is such, but also indeed how you kind of put Monique into the picture. So thanks very much for that. So are there any questions on the talk? I think. Yeah, there's.
So what is the significance of 183?
So the question is, where is this 183 coming from? So it comes from 240. So where does 240 come from? So 240 comes from the Kissing number in dimension 8. So how do you distribute perfectly 240 points? So this is done by looking at the E8 roots. So now you don't take the entire sphere anymore, you just take the upper half. And from this 240 points, if you take the cut correctly, you find 183 on the upper half.
Okay, there's one more question.
A quick question. So I imagine the reason Lovász didn't put the entry-wise non-negativity conditions which are implied on that matrix is because it would no longer be a valid bound on the Shannon capacity. So are there any SDPs that are valid bounds on the Shannon capacity and sometimes better than Lovász on any graph? On some graph, I mean.
So the question is, so the theta number gives, so the theta number gives also a bound for the Shannon capacity.
Yes,
of a graph, not only the independence.
Is there a better SDP that is always at least as good and sometimes strictly better for Shannon capacity?
I think I don't know.
I tried to find it, but I couldn't find it.
Okay.
Thank you. There are other SDP upper bounds?
Not the Hammers bound.
Is there any sense as to whether the 4-point bound, say, would potentially improve the asymptotics of the Kissing number? No, do I want to say the Kissing number? I think for Kappa-Tiansky and Levenstein, it's Kissing number, right?
Yeah, that's a very good question. Yeah. So if you can use 4-point bounds or 6-point bounds to improve the 2-point bound, which is used to prove the asymptotics for Kappa-Tiansky-Levenstein, we don't know. but we also don't believe that.
You don't believe, yeah.
Because in computations we see that these 4-point bounds are, at least the 3-point bounds we were looking at for the kissing number, they seem to converge to the 2-point bounds for large n.
Yeah.
But the 3-point bounds we computed are not really the full strength of the 4-point bounds which you could come up with. And computing these numbers is at the moment too hard.
Any other questions? Yeah.
Hi, thank you for the presentation. I had a question about this slide. So you mentioned the last sentence, some post-processing. What does that mean exactly? Or
Yeah,
can you give me an
so
idea?
first of all, we run this STP, which computes, say, the first step or the second step of Lasserre's hierarchy. So we run this on the computer, so we get some numerical data out of it. And then these algorithms, which are used for semi-definite programming solutions, they usually are giving solutions which are slightly infeasible. For example, some of the eigen. So then we take these numbers and we take these solutions and we perturb them to make them, first of all, rational, and then also, second of all, to make them really feasible. And there's an entire process of doing that. But the basic idea is that we take these infeasible solutions, perturb them slightly to make them feasible.
But usually they are always positive semi-definite, but they are not, the constraints are not correctly satisfied. But I think usually they are positive definite.
This depends on the solver. So the STP A, G, and P solver has exactly this feature.
Yeah, that's right.
But CSTP doesn't have this feature.
CSTP also has that. It's always positive.
Not in my case.
Not in your
Okay, great. So I propose let's have these deeper questions for the break. Frank, thanks once more very much for the beautiful presentation, and also for you, of course, we have some cadeautjes.
And so we're now going to start the second, last session of the CWI lectures today. And it's my pleasure to introduce Amir Ali Ahmadi. He's a professor at the Department of Operations Research and Financial Engineering at Princeton. He's also a visiting scientist at Google Brain. He received his PhD at MIT under Pablo Perillo, if I'm correct, and was a Goldstein Fellow at IBM Watson prior to joining Princeton. He's broadly interested in optimization, as we'll see, polynomial optimization and complexity aspects of that. His research has been supported by many awards or fellowships, so the Sloan Fellowship, the Presidential Early Career Award, NSF Career Award, and many others. And he's also gotten very nice prizes, such as the Informs Optimization Society Young Researchers Prize, the Best Paper Award at the IEEE Conference on Robotics and Automation, and many others. So without further ado, Amir, take the floor.
Thank you so much. Okay, so I want to thank Guido and Daniel for organizing this nice event. It's great to be here to celebrate Monique. Thank you also, Monique, for having me. So I want to talk about complexity of finding a local minimum in polynomial optimization. And everything I talk about is part of the PhD thesis of my former student, Jeffrey Zhang, who is now in the math department at CMU, and actually probably about to move soon. So the motivation for this talk is, I hope, pretty clear. And as we move to more and more non-convex optimization problems as a community, motivated by some of the modern applications, of course, there becomes a distinction between local minima and global minima. And we have a fairly good understanding of the complexity of finding global minima in various types of optimization problems. But a very natural question is, okay, for problems for which it's hard to find a global minimum, is it easier for us to find one of the possibly many local minima? And I want to give a rather complete answer to this question in the case of polynomial optimization problems. As we will see in the talk, there will be sort of two critical cases where this question needs to be studied, and these are the two parts of the talk. For the first part, I will give sort of a complete analysis and a full proof. And the second part will be much shorter, where I just sort of announce the results and give some intuition, because the proofs of the second part are a bit more technical. Okay, so let me just formalize what the setting is and what the question is. So first of all, if you're minimizing a function f over a subset of Rn, as a reminder, a point is a local minimum. First of all, if it's feasible, and then if there exists some neighborhood of positive radius, this neighborhood can be as small as U1, it just has to have a positive radius, such that if you compare your candidate point to other points in this neighborhood which are also feasible, then your point has a better objective value, or it has objective value no worse. Right? So it's a much weaker requirement than global optimality, of course, because you just want to beat your neighbors, not everybody else, which is feasible. Okay, and in this tiny example, we have these three local minima. And of course, the complexity of this question will depend on f and omega and their representation. And in this talk, I will focus on the case where f and omega are defined by polynomials. So f is a polynomial and omega is defined by finitely many polynomial inequalities. They're exactly polynomial optimization problems. And this is a sensible thing to do because, for one thing, local minima are a local notion, and on compact sets, polynomials can approximate other functions arbitrarily well. So this is a good test case. And also because polynomials are finitely parameterized, I can study the complexity of this question in the Turing model formally. So I will take as input all the coefficients of these polynomials f and gi's that are given as rational numbers. And the size of the input would be the number of bits I need to write down these rational numbers. And I have what I'm after is to find the local minimum of problems of this type. And I want to understand the running time of the algorithm that finds the local minimum as a function of the size of the input, this bit size, right? And of course, polynomial optimization, I think, is one of the favorite problems of Monique. So this is even further justification to focus on this today. Okay, so let's consider sort of the simplest cases. And typically, we fix the degrees of f and gi and study the complexity as the number of variables increases. So if you fix the degrees all to 1, then you have the case of linear programming, where the problem is convex and local and global minima are the same. And it's well known that you can find a global min, which is the same as local min, in this case in polytime. Right? So the first interesting case already appears where I keep the feasible set polyhedral. So all the gi's are still affine polynomials. But the degree of f goes up by 1, and this becomes quadratic program. Right? And it's sort of well known that already when your quadratic function has its matrix has one negative eigenvalue, global minima are NP hard to find. But it's very natural to ask, okay, what about local minima? Is it easier to find local minima? And this is the main part of this talk. I want to give you a complete proof of the theorem that answers this question. And this theorem was motivated by this question that Pardalos and Vavassis asked very explicitly in 92. So if I read the question, it literally says what I just said, that what is the complexity of finding even a local minimizer for a non-convex quadratic program? Now I'm going to talk about why they want to assume the feasible set is compact on the next slide. But I do want to make a distinction in case some of you are familiar with the sort of well-known result of Murthy and Kabadi that they also go to explain, that there's a related problem, the recognition problem, that if I give you a polynomial optimization problem, let's say a quadratic program, and a point, and I ask you, is this a point a local minimum? That was already shown by Murthy and Kabadi that this is an NPR problem. However, as is explained here, this does not rule out that there could be other local minima that are easily verified as a local minimizer, and potentially a polytime algorithm could find them. Okay. So to make this distinction even more explicit, let's look at sort of the proof that Murthy and Kabadi gave. In case you haven't seen it, is quite simple. So if you recall what a copositive matrix is, so a symmetric matrix is copositive if its quadratic form is non-negative on the non-negative orthant, so when evaluated on x's that are entry-wise non-negative, right? And they showed that that the problem of testing copositivity is NP-hard. And once you have this, this result of more think about it is immediate, because if you consider the problem of minimizing x transpose mx on the non-negative orthant, and you ask, is 0 a local minimum? So the candidate would be the point 0. Well, if the matrix is copositive, your quadratic function is 0 here and non-negative here. So this is a local min. In fact, it's a global min. Right? Conversely, if your matrix is not copositive, that means that for some point x hat in the non-negative orthant, this quadratic form is negative. But then you can just draw the ray through the origin, and by homogeneity, this quadratic form will be negative on the entire line. So arbitrarily close to the origin, you will have negative values. So the origin cannot be a local min because the value there is 0. So this is a descent direction. So that's a proof that checking whether a point is a local min is NP-hard. However, the problem we're interested in is slightly different because you don't have a point given as input. You just have the quadratic program as input. And the analogous question would be, does the problem even have a local min? Let's say if the feasible set was unbounded. And this connection between copositivity then fails. For instance, so of course, if your matrix is copositive, then the problem of minimizing x transpose mx over the non-negative orthant will always have a local min at the origin, but the converse direction fails. So for instance, this matrix is not copositive. Nevertheless, this quadratic function has a local min at a different point, at the point 1, 0. Does that make sense? So there is no one-to-one correspondence between existence of local minima and copositivity of the matrix. Okay. So the next thing I want to clarify is the precise formulation of the question. So remember, they're asking why can you find the local min of a QP over a compact set? And the reason is simply is that once you assume compactness, then you're guaranteed to have a local min, right? Because by Weierstrass's theorem, you're minimizing a continuous function over a compact set. There's always a minimizer, a global min, which in particular would be a local min, and there could possibly be other local minima. But there will always be at least one. And then if your algorithm wants to find this local min, maybe the first question you need to ask is that, will this local min have a small representation for me to return? What if local minima are irrational, for instance, or have large bit sizes? So luckily, this is not the case. So it was known already by Vavasis that if you have a QP, there is always a local min, in particular a global min, which is rational, and it has polynomial bit size. So what we're after, so this is a search problem. So we know something exists, and it has small bit size. We just want to find it. Right? It's not a decision problem. So in a sense, it's similar to the problem of finding a Nash equilibrium of a game. That is something that they always exist, and there's a search question about finding it. Okay, and here's the main theorem that gives an answer to this question. So we showed that unless P equals MP, there cannot be a polytime algorithm that finds the local min of a quadratic program. In fact, the negative result is stronger. It says not only you cannot find the local min, you cannot even get close to it. You cannot get even exponentially close. So for any constant c, fix c to be 2 or 100, there is no polytime algorithm that can return a point which is within distance 2 to the n of some local min of a quadratic program. Okay? And the main part of this talk will be to prove this theorem, and then in the last maybe 5-10 minutes move to the other case. Okay. Now, thankfully, Frank here made my job easy, at least on this slide, except that he called it an independent set. I'm going to call the same thing a stable set. So a stable set in a graph is a subset of the nodes that are pairwise non-adjacent. And the stability number of a graph, also denoted by alpha, as Frank had it, is the size of the largest stable set. So for instance, in this graph, you have 5 nodes that are pairwise non-adjacent. And you can check that you cannot do 6 vertices. So indeed, the alpha of this graph is 5. Okay? And the base of the reduction for us will be the problem of testing given a graph at an integer r between 1 and n, because alpha is obviously an integer between 1 and n. If alpha of g is more than or equal to r, In other words, does the graph have at least one stable set? Does it have a stable set of size at least R? And this is well known to be NP complete, as shown by Karp. Okay. And in fact, this is the full reduction. So what I'm going to show you is that if there was a polytime algorithm that got within distance c to the n of any local min of a following quadratic program, then this algorithm could solve the stable set problem. So what you carry over from the graph is the adjacency matrix and the scalar r, integer r. So you subtract 1/2 and you construct this objective function. And the constraints are non-negativity on the x and one last constraint which makes the feasible set compact, as requested by Pardalos and Vavasis, right? And we need to make sure this you can write this problem down in polytime, and indeed this is the case because even though you see c to the n here, the number of bits required to write this down is n, which is poly because we need order n squared bits just to write down a, so this is fine. And computing this thing of the square root of n is also fine, so trust me on all of this, we can write this problem down in polytime. Okay, any questions at this point? This is what I'm going to prove.
I mean, is there anything special about the bound, like this 3?
No, is literally, you will see in the proof, is literally the largest number you can put. The larger you put here, the stronger your result, and it's the largest number you can write in polytime. So you can improve this slightly by doing like c to the poly n, but this gives a negative enough result. So the result will be true if I put an n here, just that you don't get as good of a inapproximability result as if with this, and it's the largest number you can put and write down in polytime. It's a good question. Yes. Every c, so fixed c. Yeah, c is fixed, but you can to any number. Good question. Okay, so I'm going to prove this through a series of lemmas, and I'm going to have letters assigned to these lemmas so we can think of them in our head instead of having numbers. So the first lemma is an intermediate result, and the bulk of the proof is here, so which is about unconstrained quartic polynomials. So we're going to go to degree 4, and then we're going to come back to degree 2. And this is a decision question. We're going to show is NPR to decide, given a degree 4 polynomial, if he has a local min, right? And to prove this lemma QU, we're going to need one slide, which I put here on the board because I'm going to very frequently refer to this lemma M here. And so the departure point here is the famous theorem of Motzkin and Strauss, which relates 1 over a stability number of a graph to the minimum of a quadratic function over the simplex. In fact, for this talk, I'm not going to be using the Motzkin-Strauss theorem. I'm going to be using a reformulation of it, which is well known in the literature, and it's already in the work of the Klerk and Pesechnik, where they create a hierarchy for alpha using the Motzkin-Strauss formulation, and this hierarchy has been analyzed by Monique and Filippi here. There's certainly some connections there. But this is the lemma I'm going to be using. So first of all, given a graph, so adjacency matrix A, and a scalar K, I'm going to talk about a matrix M very frequently. So this matrix is K times adjacency plus identity minus the matrix of all ones. And then once I have this symmetric matrix, I'm going to create 2 polynomials out of it. Q is the quadratic one, and P for polynomial is the quartic one, degree 4. Q is simply the quadratic form of the polynomial of the matrix. And P, instead of x, I put the entry-wise x squared vector on both sides. So this is a homogeneous quartic, P of AK. And the lemma is the following, and this is a 3-line reformulation of the theorem. But I want you to remember that's on the board. So it says that the stability number of the graph is less than K if and only if this matrix M is copositive. So it takes non-negative values on the non-negative orthant. And if further this is strictly less than K, then this quartic form is positive definite, meaning that for a non-zero x, it takes a positive value. And this is also an if and only if, but the reason this is in gray is that I'm not going to be using this implication. I'm going to be using the other three. Okay, and this is on the board. All right, so the first lemma we want to prove is that for a quartic, is NPR to test if there is a local min. And this is how we're going to prove it. We're going to show that if you're given a graph G and an integer R, you can test this question alpha more than R if and only if this quartic polynomial with K replaced by R minus a half has no local min. So the fact that I'm subtracting a half is, the half is not important. You can subtract any other rational number you want less than 1, but it is important that you subtract something, and this will become hopefully clear. All right, and this will follow if I can prove the following slightly more general statement, that for a non-integer scalar k, alpha is more than k if and only if PAK has no local min. So PAK is a quartic defined by the adjacency matrix, and then rational but not integer number k. Okay? Why does this imply that? Because if this is true, I can then apply it with k equal to R minus a half. I'm going to get that this polynomial has no local min if and only if alpha g is more than or equal to R minus a half. But because R is an integer, that's the same thing. If you're more than R minus a half, you're more than R. So this is the same thing. Okay, so now my goal is to prove this. I call it the non-integer lemma. For any non-integer scalar k, alpha is more than k if and only if PAK has no local min. So one direction is easy, and it doesn't use the non-integer fact that if alpha is less than k, then PAK is positive definite. If PAK is positive definite, x is a 0 is a local min, right? Because the form vanishes at 0. If it's positive everywhere else, this is a global min. It's definitely a local min. Okay. Now what about the converse? So now if alpha is more than or equal to k, then because k is non-integer, then I can say alpha is in fact strictly more than k, because alpha is an integer and k is not. Okay. Then I use lemma m again, the first case, and I can conclude that this matrix M and K is not copositive, right? Which is the same as saying this quartic form is not non-negative. So sorry for all the negations. Which means that 0 is not a local min, right? Because if this quartic form is not non-negative, that means at some point in space it goes negative. And again, I can connect it to the origin. On the entire line, you will be negative. Arbitrarily close to the origin, you will be negative. So 0 cannot be a local. But have I established this converse direction? Of course not, right? Because what I want to show is if alpha is more than or equal to k, then this polynomial has no local min whatsoever. The only thing I've done is that I've shown that 0 is not a local min. So now I need to worry about every other point in Rn, right? But let's remember that any local min must satisfy, let's call it x bar, must satisfy first and second order necessary conditions. So the gradient should vanish, and the Hessian of this quartic should be PSD at that point. So if we can somehow show this stronger result, we would be done. And this is the last lemma of this one is lemma 0, which says that for a non-integer scalar k, 0 is the only second order point of this quartic polynomial. So in fact, no other point is even a second order point, so it cannot be a local min. 0 is the only second order point, but we separately show that 0 is not a local min, so we would be done. Okay, so now the goal is to prove lemma 0, which is very easy to state. Is if you have a non-integer k, and you construct this polynomial of degree 4, no point in Rn, 0 will be the only second order point. Okay? And this is where it gets kind of interesting. So I'm going to need some notation. So for two vectors A and B, or for two matrices A and B, this notation is the entry-wise product. Okay? And I need some other notation here. So if x is a vector of length n, x bar is also a vector of length n, M is a symmetric matrix n by n, and G is a graph on n nodes. This notation is a restriction notation to the support of x bar. So let's think x bar is a vector of length 10, but it has 3 non-zero elements. Let's say entries 2, 5, and 7 are non-zero. Right? Then this x sub
x bar will be a vector of length 3, which has, in those 3 entries, has entry 2, 5, and 7 of x bar, right? Similarly, M sub x bar will be a 3 by 3 matrix instead of a 10 by 10 matrix, which is a principal subblock. So it has rows and columns indexed by 2, 5, 7. And finally, G of x bar will be an induced subgraph. So you take just these 3 nodes in your graph instead of the 10 nodes. You keep all the edges between these 3 nodes, and you throw everything away, everything else away. Right? So this is what this notation means. OK. So what am I going to do with this notation? So we want to prove 0 is the only second order point. So let's compute the gradient and Hessian. And I want you to trust me on the algebra. So you can do, so with this notation, this can be conveniently written like this. You can do some sanity checks. So if P has homogeneous and degree 4, the gradient should be homogeneous of degree 3. And it is. And the Hessian should be homogeneous of degree 2. And it is. So this notation creates a diagonal matrix out of a vector. That's what this means. Okay. And now let's see. So suppose, for the sake of contradiction, that there was a non-zero point x bar, which was a second order point. Okay. Now at this point, the gradient should vanish. But let's look at what happens if the gradient vanishes. And if we plug in x bar, and then we restrict this vector to the support of x bar. Because it's an entry-wise product, if the entry-wise product is 0, that means on the entries where x was non-zero, this other vector should vanish, right? So this is what this says, that this other vector, when restricted to the support of x bar, should vanish. But that simplifies the Hessian, so I'm also going to evaluate the Hessian first at this point and then restrict it to the principal subblock given by the support, and the second term will go away because of this, right? So the Hessian, when restricted and evaluated x bar, will be this expression. Because the Hessian has to be PSD, its principal subblock needs to be PSD. And this implies, by a simple linear algebra argument, that MAK sub x bar is PSD. So this is the only thing we need to remember from this slide, that if there is a second order point, then I can take this matrix MAK. So a reminder of what's the definition of MAK. I can write MAK based on the graph and the k, which is non-integer. So this matrix as a whole, it may not be PSD. It may not even be copositive. But there is a principal subblock of it, which corresponds to the support of x bar. That subblock will be PSD. OK.
Why did the diagonal matrix?
Because of this. Because this is diagonal produced by this vector. And this vector is literally 0.
Oh, by definition. Yes.
Yeah. Sorry, I know the notation is a little hairy now, but it's the last slide with heavy notation. So, okay. So now so we established that this principal submatrix is PSD. Now the other very natural thing to do is let's look at the graph restricted to x bar. So let's look at the induced subgraph gx bar, which I only pick the nodes where entries of x bar are non-zero, right? And I can play the same game. I can write this matrix for that smaller graph. It will be a smaller matrix. And it's easy to see that that's the same as picking the old matrix because of this definition and restricting that matrix to x bar. This is what on the previous slide we showed is PSD, but that implies that the M matrix for this smaller graph is PSD. A PSD matrix is definitely copositive. And if I'm copositive by lemma 1, one more time, alpha is less than k. So for the smaller graph, alpha is less than or equal to k. Okay. Oh. Now, there's one more nice property that this matrix has. It is PSD, but it has an interesting vector in its null space. In particular, x bar squared restricted to the support of x bar, right? So in the first equality, I'm just replacing this matrix by that. In the second equality, this is just some algebra on how you can distribute this restricting operation. And the last equality comes from the previous slide that the gradient vanishes, right? That's the question that Daniel asked, right? But why is this interesting? Because if you look at now this quartic polynomial restricted to this adjacency matrix, so this is a quartic polynomial in fewer variables, right? In the variables in the support of x bar, this has to be 0 at this vector because this polynomial is nothing but this vector multiplied on the left by the same thing transpose, by the x bar squared x bar transpose, right? Okay, but that means that this polynomial is not positive definite because it vanishes at a non-zero point. And one last time by this lemma, the counterpositive, I have that alpha of this smaller graph is more than or equal to k. So the opposite inequality. You can probably see the contradiction. So this has to be equal to k, but k was not an integer, and the stability number is an integer. Right? So that's a contradiction. So what did we establish? We succeeded in proving lemma QU, quadratic on constraint. So if you have a quartic polynomial, is NPR to test if there is a local mean. Okay, so now we're done with quartics, and I want to go back to quadratic programs, and this will be more straightforward. So now I want to go back to this notation of the Q, which is a quadratic form, right? And the first lemma, I'm going to call it lemma E for existence of local minima for unbounded QPs. And it says it's NPR if you have a QP over a unbounded set, unbounded polyhedron, to test if he has a local min. And the reduction is very straightforward. So you start with the graph and n vertices, and you want to test if alpha is more than or equal to r. Once again, you subtract a half first. So k is r minus a half. And now you put in your objective the quadratic function qak, which is on the slides. And we just proved that alpha is more than r if and only if this quartic function has no local min. But it's very easy to see that this will happen if and only if this quadratic program has no local min. Why is that? Because for any point x which is feasible, x would be a local min for this QP if and only if the entry-wise square root of x will be a local min for this quadratic function, right? Because it's easier to see the counterpositive of this. So for instance, if this x is not a local min for this QP, that means there is a sequence of points approaching it which are all feasible, all non-negative, but having value less than at your candidate point, where you can take this sequence, which is the square root of the previous sequence, and that sequence will converge to square root of x and contradict that square root of x is not a local min, and this goes in both ways. Right? Okay, so the thing to remember from this slide is that we can also check if alpha is more than r by checking whether a quadratic program has a local min. Once again, you subtract the half and you put that in the objective. Okay, and now I'm finally back to the main theorem. Remember, the question as proposed was that you need the feasible set to be compact. So when the feasible set is compact, you cannot, it doesn't make sense to ask, is there a local min or not? Because the answer is always yes, right? So now this is a search question. It's just about finding this local min. And I already gave you the reduction at the beginning. Now I'm going to argue why the reduction is correct. So this is the objective function. The 1/2 has already been subtracted. So k is r minus 1/2. And let's see why this works. Okay. So if you have this quadratic program, and remember, I claimed that if you had any algorithm that then went within distance 2 to the n or c to the n of any local min, that algorithm would decide which case you're in. Is alpha less than r or more than or equal to r? Right? And that would be the end of the reduction, right? So the reason this happens is that if alpha is less than r, I can claim that the QP has a local min, which is at the origin of this, and this is the unique local min. Why? Because if alpha is less than r, then alpha is an integer. It has to be less than r minus a half, right? Which implies that this quartic form would be positive definite. So one last time, this is by this. Right? So which implies that this objective function is strictly positive on the feasible set. So you're 0 at 0 and everywhere else positive, so 0 has to be a local min. Why is it the unique local min? Where if you, let's suppose you had another local min, then if you draw the line to the origin, because you're positive here, the quadratic function on that line looks like this. So if I multiply my point by like 0.9, it's going to take a smaller value. So it cannot be a local min because that's the descent direction. So this is the unique local min. Okay, what about the other case? If alpha is more than or equal to r, then I claim that all the local minima have to be on this orange line. So there could be multiple of them in this case, but they all have to saturate this last constraint. So why is that? That's because of the proof of the lemma E, the unbounded QP, because we just proved that if alpha is more than R, if you remove this last constraint, there are no local minima. That's what we proved, if you remember, right? So now that the feasible set is compact, there have to be local minima. What choice do they have? They must be on this line, because if they were anywhere else, let's say they were here or in the interior, then there would have also been a local min for the entire non-negative orthant. And that we ruled out, right? So all the local minima have to saturate this constraint. Okay, so now we're done, because suppose there was a polytime algorithm that, given any quadratic program, landed within distance c to the n of one of its local minima. So take that algorithm and run it just on these quadratic programs. What is it going to happen? So on these quadratic programs, the local minima is either at the origin or they're here. The distance from the origin to this line, and this goes to your question, is 3 times c to the n. So if the algorithm is going to be within c to the n, is never going to land in the white area. So that comes as a guarantee, because it always has to be within c to the n of some local min. So if the local min was here, the algorithm would end up somewhere here. If the local min were on the orange line, the algorithm would end up somewhere there. Well, we can run the algorithm and then see where it lands, and based on that, reverse engineer this and see, okay, are we in this case or in that case? Right? Okay, so the wrong direction. So this is the end of the proof, and to recap, so we had this lemma M, which is on the board, and we proved it many times, to prove lemma 0, which is that 0 is the only second-order points of these quartic polynomials. And that allowed us to prove the non-integer lemma, which is that if k is non-integer, and this was important, then we can relate the stable sets to local minima of these quartic polynomials. And this allowed us to prove that for an unconstrained quartic, testing local minimality existence is NP-hard. This allowed us to prove lemma E, which is about existence of quadratic programs in the unconstrained case, and finally the theorem. And the reason I recap this, in case you haven't noticed it, is that as many theorems in polynomial optimization, there is an influence by Monique, and in this case it's very direct. But sort of more seriously, I want to use the opportunity to thank Monique for. Okay, yeah, this took me a while to engineer. So I think the first time I met Monique was at this workshop at the Wolfpack, where it was about an STP workshop where there were 4 instructors. Frank is also here, and at that time I was a graduate student at MIT. I don't know if you remember, when we had problem set sessions after the talks every day, and I remember Monique's problem sets were very difficult, and she would give no hints. So at the beginning, our relationship didn't go so well, but that has changed over the years. I'm joking, of course. And this is our last encounter was from last week, where Monique came to Princeton and gave 2 fantastic talks. So congratulations on becoming a fellow here and on all your amazing lemmas and theorems. So I'm not desperately short on time, so I'm going to. I may not get to the last part, but let me. This is more of a discussion slide, which I sort of found interesting as I was making the slides. So because if you see this theorem and you came with the mindset that, okay, of course local minima should be easier to find than global minima, and now here I am telling you, no, they're not, and not only they're not easier, you cannot even get exponentially close to them, right? So your reaction may be that, okay, but maybe this is the worst case result, and NP-hardness doesn't happen in practice and things of that sort. So I want to discuss this a little bit by making a few observations. So first of all, there are a number of results in the theoretical computer science community that say if you have any NP-hard problem, that it cannot be that the only hard instances are a few, like this, and this can be formalized. Then let me just say what this implies for this problem. So an implication of this result plus these other theorems is that if you pick any polytime algorithm which attempts to find the local min of a quadratic program, So let's say this is the gradient descent algorithm with projection to the polytope, or is some sort of semi-definite relaxation, any algorithm, as long as it runs in polytime. And now you can see, okay, out of all the instances that I can write down with k bits, so there will be 2 to the k such instances, on how many of them will this succeed and how many of them will it fail, right? And all the 2 to the k instances, this algorithm must fail on a number of instances which is larger than any polynomial in k. So you cannot bound the hard instances by a polynomial. So there will be some large super polynomial number of instances where your algorithm not only will not find the local min, but it will land exponentially far from any local min. At the same time, I find this other claim contrast interesting, and this is when you study things in sort of the real model and you ask genericity questions versus NP hardness results, right? And I cannot make this connection for the problem that I described, but I can make it very precise for a simpler problem, which I had on my beginning slide. This is the result of Mordi and Kapadi, right? So if you have a quartic polynomial and a point, this is a recognition problem, is NP hard to check if x bar is a local min, right? This is how I had on the first slide. Hence, by the same claim that I told you, any polytime algorithm would fail on a large number of instances, on super polynomial number of instances. Yet, for a generic quartic polynomial, so if you generate P randomly, let's say, then a point is a local min if and only if it satisfies the gradient vanishes and the Hessian is positive definite. And this can be checked in polytime, right? Because this you have n leading principal minors, right? So where is the catch? So the catch is that we are in completely different spaces, right? So when you implement these questions on a computer, you are not in the real space, right? So the inputs are rational. So all the inputs have measure 0 in the set of all real inputs, right? So within this measure 0 set, we're counting a subset. How many of them is your algorithm succeeding, right? So there is no contradiction here. And in a way, this sort of saying that these problems are generically easy, they only apply if you had a real machine computer, not a digitized computer where you were implementing the algorithm on with floating arithmetic and rational numbers, right? And there are other theorems in our community like this, like a very well-known one is this really nice result of Jawang-Ni, which says that under the Archimedean assumption, so this is more for the experts, I apologize if you're not familiar with this, the Lasserre hierarchy has finite convergence generically, right? But this is sort of the same situation. What if we run the Lasserre hierarchy on a digital computer, which we do all the time, right? And the input is rational, then the statement doesn't tell us, on how many instances you will succeed or fail. And to my knowledge, the complexity of testing finite convergence is not known or anything of that. So I think it's best if I completely skip the last part of the talk. So I apologize for that. But the last part was actually more positive. There's a positive result about cubic polynomials where you can find you can both solve the recognition problem. So if you have a cubic polynomial, you can test. And why cubic? Because this is sort of the only case left in polynomial optimization, if you think about it. So you can solve the recognition problem given a point, is it a local min? You can also find the search problem given a cubic, tell me if it has a local min, and if so, return one. You can do this with semi-definite programming. And sorry for the mistiming, but let me just go to my last slide and tell you that if you're interested, this is the second paper is about the cubic polynomials. Thank you.
So there's definitely time for questions. Anybody?
It seems to me that the quadratic example you construct has that exponential in the bit in the data. So what is the relation to the bit size?
No, that's fine because okay. So it's a good question. So let me go back because the claim is that if you have a polytime algorithm for any quadratic program, right, that would get within exponential distance of a local min, then P equals NP, right? So that that statement is true independent of like what quadratic program I wrote down, right? So that is just a proof technique because I can show that I can give a polytime reduction. So you're right that you get the exponential result if you put this number here, right? But the fact is that you can write this number in polytime. And so there's no issues with putting this number here, but you can put any other number here, like Danielle said, you can put an n here, right? And you can ask, okay, if I restrict myself to even more QPs that maybe all their magnitude of all these entries are bounded by the dimension. That would be a separate question, right? And what this reduction would tell you that you cannot then get within, I believe, root n of a local min, right? But the statement I said is correct. If you consider all QPs, you cannot get within 2 to the n of any local min. But if you put further restrictions, now only want QPs whose numbers are by magnitude bounded by n, then this will no longer be a valid reduction, but you can put n and then you get that you cannot get within root n. That's also in our paper as a corollary.
Is there hope that if P is NP, that is a problem with that algorithm?
If P equals NP, there's certainly for stable set, but I'm not showing completeness here, right?
Yeah,
so
for any matrix, this is for any quadratic program. Or
So if P equals NP, can we find local minima in polytime, right?
Yeah, or
so,
at least the question you posed there,
Yeah, no, I because here I'm just showing NP hardness. I made no statements about completeness or membership in NP.
Yeah.
So it doesn't follow. It could. I mean, I believe it would, but and I believe P is not equal to NP. But hypothetically, it doesn't follow directly, right? Because I haven't shown that this problem is in NP. But hold on. But the copositivity problem would be solved, and the recognition problem would be solved.
But it is for any quadratic program,
Yeah.
This, not just for copositive programs.
Yes. So that's why I don't see. So if P equals NP, can we find a local min of a?
Can you find with small bit size? I guess. That's the question then.
Yeah, so such a thing would always exist, and I don't think it would it follow that actually it would follow, right? Because of Avasis's result, right? That there's always a certificate of small bit size, right?
Oh,
so
yeah,
Avasis says quadratic program is in NP, so of course, if P equals NP, then quadratic program is in NP.
Yeah.
Yes, so not by this, but by Avasis's
You
theorem.
can certify that it is a minimum then.
Yes, yes, but nothing by what I said is by a result of Avasis.
Okay,
the
yeah,
title of the
yeah, you're
paper
right.
is QP is in NP. Yeah. Sorry, I got confused.
Actually, can't stop myself from asking a question. Sorry. So, in the generic case, it's still not clear whether you can certify that
Whether you can find local min.
Yeah, or that it exists. Right?
No. So that's why I only made the connection to the recognition problem.
Like for a specific point.
Exactly.
Yeah.
Exactly. So
it
in the generic case, is that's true? Where was it? But even in the generic case, I don't know how you would find the local min generically.
All right. So if there are no more questions, let's thank Amir one more time. And we have presents for you, so don't escape too quickly.
All right. So our next speaker is Reka Thomas. Reka is a professor at the University of Washington. She received her PhD in operations research at Cornell under Bernd Sturmfels, and was a postdoc at the Cowles Foundation of Economics at Yale. She also spent time in the Zuse Institute in Berlin, and she's currently the Walker Family Endowed Professor of Mathematics at the University of Washington. She's also a fellow of the American Mathematics Society and was an invited speaker at the International Congress of Mathematicians in 2018. and she's also broadly interested in optimization and algebraic geometry. And I guess I know Rekha's work a lot in the context of extension complexity, particular characterizations of semi-definite extension complexity, as well as relatively recently she has this very nice work on explaining Razborov's sort of flag algebras for estimating all sorts of properties of graphs using symmetry reduction and sums of squares representations. So today she's going to talk to us about graphical designs. So take it away.
I think I met Monique a long time ago when I finished my PhD. We were also at some Oberwolfach meeting, and I remember exchanging information about the measure zero set of places that you could live at in New Haven, Connecticut. So I was a postdoc there with Scarf for a short time, and the office person took out this big map, crossed out everything, and said, you can only live here. And I had an apartment there, and I think Lex and Monique had that information later. But I really met Monique only like 15 years ago, maybe, when I started working in polynomial optimization. And she has done really influential things. In particular, there are two papers that I keep looking at. One of them Frank already mentioned, the one that lays out all the different lift and project methods. I think this is like for the generations, because it just really explains how all these different methods compare and contrast, and it's much, much, much easier than trying to figure this out yourself. The other paper I think that's also for the ages is the big survey on moments and sums of squares, which I seem to download every year. I don't know why, but it's definitely something that all beginning students should read. It has everything, it's completely correct, it's so detailed, it's amazing that such a paper exists. So yeah, very influential. I am not going to talk about polynomial optimization today. I'm going to talk about graphs and polytopes and other combinatorial things, which I think are also close to Monique's heart. And this is more recent things that I've been doing, so I'm personally excited about it, so I will talk about this, okay? So I'm going to talk about something called graphical designs. Okay, so this is a joint work with the people you see here. So graphical designs were defined by Stefan Steinerberger, who is my colleague at the University of Washington. He's a harmonic analyst. And on the left here is my student, Catherine Babecki, and the work I will present is joint work with both of them in different papers. Okay, so Stefan was motivated by the notion of spherical designs to create something called graphical designs. Let me quickly remind you or recall what a spherical design is, and then we'll use this, put this on graphs. Okay, so a spherical design is a quadrature rule. So it is a collection of points on the sphere, say x1 through xn, and they come with weights. So these weights are real numbers. Let's call them a sub I for each xi. And the property they should have is that if you have a smooth function f, sufficiently smooth, then the global average of the function on the sphere, which is what you see on the left, is the same roughly as the weighted average of the function values at these points xi. Okay, so that is a quadrature rule. And of course, huge staple of numerical integration. You know, people really like these. On the sphere, the right functions you want to integrate are the spherical harmonics. The spherical harmonics are homogeneous polynomials graded by degree, but they're harmonic, meaning that they are annihilated by the Laplace operator. And spherical harmonic means they're actually eigenfunctions of the Laplace operator. Okay, so you can just think of them as polynomials if you like. And then because of the grading, there's a natural order in which you want to integrate. You want to catch as many polynomials, you want to catch as high a degree as you can among the different polynomials, okay? So this definition, spherical T design, means that you have a design that integrates all polynomials of degree at most T, all spherical harmonics. And on the picture here, you see a spherical 5 design. So these are the vertices of a regular icosahedron that's inscribed inside the sphere. And if you just take the function values there with uniform weights, then you will get the same thing as integrating the, any polynomial of degree up to 5 on the entire sphere, Okay? So this is the notion of spherical design. And so what Stefan decided was he wanted to put this on graphs. He had already figured out how to do this on other manifolds like tori and so on. So he decided to put this on graphs, and so let's do that. Okay, so for this talk, I'll keep the graphs very simple. Let's take them to be finite graphs, simple, connected, and very soon I'm also going to assume regular, but none of this is really required. The theory is very general. And so now we have a function on a graph. So like this f function over here, that just means I have a function on the vertices of the graph. I have some real numbers on the vertices. And we say that a set W of the vertices, subset, with some weights, which I'll call AW, they average the function if you do the same thing as we saw before. So on the right here is the global average of the function on the graph. And I want that to become equal to this weighted average over the W vertex. Okay, so we're interested in sets like this W with the weights. Okay, so here's a quick example. So here's the Peterson graph, and here you see a function on the graph. If you quickly add up these numbers, you'll see they're 0. They add up to 0. So the global average of the function on the graph is 0. And on the left here, you see one design, these red dots with uniform weights. And if you just add up the weighted average, you'll see 2 minus 2 minus 1 plus 1. It also adds up to 0. Okay, so on the left is a uniformly weighted design. And on the other side, which is hard to see with the colors, is not uniformly weighted. So now I have some weights that are 1/3 and then another weight that's 1. And it's depicted by these pink colors, which are difficult to see, and then this is the 1. So the pink is the 1/3. So this is a slightly smaller design because I'm allowing non-uniform weights. And again, the weighted average over those points is 0. Okay, so this is the notion of a design. This is the notion of average. I haven't quite defined design yet. I'll talk about the functions in a second. Okay, I haven't told you which functions we're going to do this for. So I'm just giving you one example of a function and something that averages it. Right. So yeah, good question. So the next question we can ask is which functions do we want to average? So in the case of spherical designs, it was the spherical harmonics. And so the natural guess here is let's work with the eigenvectors. Let me go back, yeah. So I'm going to use the natural thing to do here is work with the eigenvectors of the graph Laplacian. Because in the spherical case, we were taking eigenfunctions of the Laplace operator. So now let's go to the Laplacian of the graph. But because I'm going to assume that my graph is regular, it doesn't matter whether you use the Laplacian or you use the adjacency matrix or a scaled adjacency matrix or whatever. The eigenstructure is the same. The eigenvectors are the same. So in this example, let's go with not in this example, for the talk, let's go with trying to average the eigenvectors of AD inverse, where A is the adjacency matrix and D is the diagonal matrix, whose diagonal entries are the degrees of the vertices. Okay? But this is a regular graph. So this is just a scaled identity, okay? So we're going to average these eigenvectors. These are the functions that I will take. And that's enough because it's an eigenbasis. So any function is a linear combination of these. So it'll be enough to do that. So one special feature about this particular matrix is that this is doubly stochastic. So the rows and the columns sum up to 1. So because of Perron-Frobenius, we know that that means the spectrum lies between -1 and 1. Okay, the biggest eigenvalue is 1. It's always attained. I'll call this the trivial eigenvalue. And then all other eigenvalues have absolute value less or equal to 1. Okay, so the spectrum lies inside this interval. Good. So here's an example. So here's the icosahedral graph on the left here. And in this case, this has 12 vertices, so we expect 12 eigenvectors. And they're also orthogonal because my matrix is symmetric. I can choose an orthogonal set of eigenvectors. So here they are. So in the rows of this table here, you see the different eigenvectors. This number phi and the number psi are these irrational numbers that you see up there, okay? In this example, you see immediately that there are 4 eigenvalues, and they come with multiplicity. Okay, so they do lie between 1 and -1. The first eigenvector that comes with eigenvalue 1 is always the all ones vector, so that one is trivial. And all the other eigenvectors, all the other rows of the matrix, because of orthogonality, they have this property, right? 1 transpose times any other fj is equal to 0, okay? But this is very convenient because this quantity is also the global average of fj, right? So if I want to take the global average over the whole graph, I'm just doing 1 transpose fj because I'm just adding up all the values. So this is very convenient because now the global average of all these eigenvectors except the first one is 0, okay? So I don't have to think about what that number is anymore. All right, so this is good. We have all the eigenvectors. So the last thing I need to tell you is what order should we try to do this in, right? So before we had this natural order given by the degree of the polynomials. Now I don't have any such natural order. And the order I'm going to use is the one that you see here. So if you notice the way the eigenvalues are written, they're written in decreasing order of absolute value. So the first one is 1. Then these 2 eigenvalues tie in absolute value, so you can break the tie any way you want. But the next one is definitely smaller, okay? So we're going to put them in decreasing order of absolute value. And this order is actually kind of natural for the analyst, so at least for Stefan, this was natural. He calls this the frequency order. And I'll try to motivate this just with some examples of why this is. So this order is supposed to capture the smoothness of functions on a graph, okay? So here's a picture of the United States graph. This was apparently made by Donald Knuth, this graph. So recently, there was a short article by Catherine in the AMS Notices, and Knuth wrote to her and told her that this graph was his. So we know now this is made by Donald Knuth. Anyway, so this is from Mathematica. So what's going on here? So we have a vertex for every state, and there's an edge that connects to vertices if the state share a border. And here, for instance, this is not a regular graph, so the first eigenvector is not trivial. So you already get some information there. And here's the first eigenvector. So the colors show you the different magnitudes of the numbers. And you see it's fairly smooth as you go across the graph. That's the first eigenvector. Then here's the second eigenvector, also still fairly smooth. The ordering of the eigenvalues are like this. Okay, so we are ordering the eigenvalues by absolute value. And now if we go further, so here, for example, you see the 11th eigenvector, and you see this jumps quite a bit. Okay, so the smoothness is nicely captured by this ordering on the absolute values, on the eigenvalues given by absolute values. So we call this frequency order. And the general idea is, like in Fourier analysis, if you have a relatively smooth function on your graph, meaning the function value doesn't change too much when you jump from one vertex to the adjacent one, then you expect that most of that function is made up of these low frequency eigenvectors. So we would like to catch as many of the low frequency eigenvectors as possible in this averaging game. Okay, so this is one natural ordering. In this combinatorial setup, it doesn't matter which ordering we use, but I will use this ordering in the talk. Okay, so this is called frequency order. Yeah, question? Yeah. When you get which one? -1. Say, oh, you mean all the way to -1? Yeah, it's not exactly a precise theory. So it's sort of respecting the structure of the graph. So for example, if you had a bipartite graph, then you would have eigenvalue 1 and eigenvalue -1. And in that case, this picture would look exactly like one color on one side and another color on the other side. But it does respect the structure of the graph. So it's sort of smoothness modulo the structure of the graph, roughly. It's not a very precise theory, okay? But generally, this is the type of picture you will see, that the smoothness is captured by the ordering of these eigenvectors, eigenvalues. Okay, so we have this notion. So here now I can define what a graphical design is. So the definition goes like this. So we start with this graph and we order the eigenspaces. So these big lambdas are the eigenspaces. And let's assume that there are m distinct ones. So the graph has n vertices, but there are m distinct eigenspaces. And I'll always assume that the trivial one is the first one. But after that, you can put it in any order. For the most part, I'll do this in frequency order. Okay, so we order the eigenspaces. And then a K graphical design is some subset of the vertices W with weights that averages the first K eigenspaces. Okay, so we want to capture entire eigenspaces at one time because we don't want to worry about which eigenbasis we're using in each eigenspace. And also, this makes sense when you have eigenvalues with multiplicity. This makes better sense than to go eigenvector by eigenvector. Okay, so this is the definition. And this is due to Stefan. It's actually from like 2018, but the paper appeared in 2020. Okay, so having made the definition, now you can worry about different types of weights. So there are different types of designs. So if the weights are just any real numbers, then I'll just call it a weighted design. This is not so attractive for people who do quadrature. They don't like negative weights typically. More interesting or much more interesting for them would be positively weighted designs, so where the weights are non-negative. And then if you're a combinatorialist at heart, then you might look for a 0-1 weight or a uniform weight. And in reality, you'll see that this last one, while it's very appealing combinatorially, it's quite restrictive. And so the middle one seems to be the right balance. Okay, so we want to look for non-negative weights and that can average the first K eigen spaces. Okay, so that's a K design. So here are some examples. So back to the icosahedral graph, and here I've ordered the eigenspaces like this. So before I had them ordered in frequency order, now I jumbled it up a bit. So lambda 1 is still first, then I put the last one next, and so on. Okay, so it's some order. And then on the left here, you see a arbitrarily weighted design. So this one has both negative weights and positive weights. The negative weight is blue. The non-negative weights are pink or red, depending on the magnitude. Okay, so that's one. And here's a positively weighted one. It needs more vertices because I'm putting more restriction on the weights. So that one requires 9 vertices, whereas the first one only required 7 vertices. And then finally, here is a combinatorial design. And this combinatorial design actually cannot average the first 3 eigenspaces. It can only average the first and the second, okay? In fact, there's no combinatorial design that can average the first 3 eigenspaces. So this is why what I mean by it's more restrictive, like you don't want to insist that your weights are uniform, okay? So this is an example of these designs. Okay, so last definition is oftentimes we're also interested in what's called an extremal design. So these are designs that can catch all eigenspaces except the last one. Okay, so you decide the ordering first on the eigenspaces, and then we say we want to get everything except the last eigenspace, and you cannot have any proper subset that can average all eigenspaces. So this is a fact. So this is the best you can do, these extremal designs. And of course, this depends on the ordering you put on the eigenspaces, and this was defined by Konstantin Golubev in 2020. And he makes some nice connections to graph theory, like to graphs that meet the Hoffman bound and Chiga bound and so on. So he has a very combinatorial paper on these extremal designs. Okay, right. So let's come to the questions. So the questions we wanted to ask at the beginning was, can we compute these? How do we compute these K designs? Can you compute the smallest K design? That would be most interesting. And then maybe more ambitiously, is there a way to organize all these designs in some clever way? Okay. So again, if you sort of remember the formulation a little bit, or maybe I'll just say it, is that so computing these designs, depending on which kind of weights you're looking for, is either a linear algebra question or a linear programming question or an integer programming question. But as soon as you say that you want the smallest, then you're putting sparsity on top of that problem, okay? So then the problem becomes hard because even finding a sparsest vector in a subspace is difficult. So even the linear algebra version becomes very hard as soon as you ask for smallest, okay? So we thought about this for a long time, didn't make any progress. But then at the end of the day, we figured out that there's a way to do the last one. So there's actually a structure on all these designs, which is maybe a way to optimize. So let me explain that theorem next. Okay, so here's the main theorem. This is, I'll call this the structure theorem. So we proved that the minimal positively weighted K designs. So from now on, I'll mostly only talk about positively weighted designs. So minimal means that it's minimal by inclusion. So minimal positively weighted K designs are in bijection with the facets of a polytope. Okay, so there is a polytope you can construct so that the facets contain all these minimal positively weighted designs. And the bijection is sort of complementary. So if you have W, a K design, then V minus W, the complement of W, are the vertices that index the facet, or they're the indices of the vertices on that facet, okay? So you'll see many examples. So if you want a small design, if you want W to be small, that means you want V minus W to be large. So we're looking for facets of this polytope that has lots of vertices. In fact, the maximum number of vertices. So how do you do that? How do you find facets and polytopes with the maximum number of vertices? That's really the equivalent question to sparsity, okay? So if we wanted sparse things on the left, we're looking for facets with the maximum number of vertices, okay? So here's a little cartoon that shows you, it's not a cartoon, it's actual picture of designs in the octahedral graph. So these are some extremal designs in the octahedral graph, and you see the polytope is a triangle. Facets all have the same dimension on the polytope, right? So by facet, I really mean the maximal dimensional faces, okay? So all the faces do index designs, but the minimal ones are indexed by facets. So in this picture, you see the facets, which are the lines. They index the minimal designs, but if you go to the vertices of this polytope, which are faces, they will also index designs, same type of designs, but they're not minimal. They contain more vertices. Okay. So this is the theorem, and so I mostly want to just illustrate this theorem on a few examples, just so you see how the theorem works. Okay, so I won't say much about the proof, but here is an illustration of the theorem. Okay. So first of all, let me give you a recipe to construct the polytope, and then we'll see examples. Okay? So these polytopes are known as eigenpolytopes. A version of them, or at least the version we need, is a slight elaboration of what's originally called eigenpolytopes. They were defined by Chris Godsell, who's a graph theorist from Waterloo, in his thesis from 1978. And the recipe is like this. So suppose I want to average the first K eigenspaces. Then I break up. So this matrix here is the full matrix of eigenvectors. This is a square matrix, and the matrix is banded according to the eigenspaces. Okay, so suppose I want to average the first K eigen spaces. Then I have one set which I'll call K that contains lambda 2 up to lambda K. So ignore lambda 1 because lambda 1 is special. So put lambda 1 with the complement. So I have K, which is lambda 2 to lambda K, and then K bar is everything else. And then we color the entire eigenvector matrix according to the ones we want to average and the ones we don't want to average. Okay, so the blue ones we want to average, these eigenspaces. The pink ones are the complement. Okay, now we split this matrix apart into two parts. The pink ones go up there and the blue ones go down there. Ignore the blue, go to the pink part. So this is the part that we don't want to average. Okay. So that's I'll call this UK bar. And now switch from the rows of this matrix to the columns of this matrix, okay? So that's some configuration of points that live in space. And then we convexify those points. That is this polytope, okay? So graph theorists do this. They do construct this type of polytope, but they don't do it for multiple eigenspaces. They usually do it for one eigenspace. And this has some important consequences in spectral drawings and things like that. So people who are interested in this, Gotzel and his collaborators have several papers on these eigenpolytopes. Here, the slight variation is that we're stacking eigenspaces together, okay? So this is the recipe. So we take the part of this matrix that we don't want to average, put it together in a matrix, and then take the columns, convexify. That's the polytope, okay? So now let's see an example. So here's back to the icosahedral graph. So in this graph, say suppose I want to average lambda 4 and lambda 3, which are here. So if we ignore this, and then take the parts we don't want to average. So lambda 2, I don't want to average, that's this band. But we always throw in this all ones vector on top, okay? You'll see why in a second. And now we take the convex hull of this part, the pink part that you see here, okay? So you can ignore this one, the first row, because it's just embedding the whole thing at level 1. So ignore that. So what we expect is some 3-dimensional polytope, right? Because these are all 3-dimensional vectors. So I expect that. And if you do the convexification, then by miracle, you get the icosahedron again. Okay, so this is a miracle of graph theory, and there's a reason for it. The people who study eigenpolytopes understand this. But you do get the icosahedron again, which is coincidence. And now my theorem says that the facets of this icosahedron index the minimal designs that can average these 3 eigenspaces, lambda 1, lambda 4, and lambda 3. Okay, so let's just check. So every facet in the icosahedron is a triangle. So the complementary set is the design. So in this example, I can draw the graph and the polytope all together because I got the icosahedron again. And the complementary set, which is colored here in the back, you see, is a design that can actually average the first 3 eigenspaces. Okay? So lambda 1 is counted with the bad part, with the pink part, but everything can average lambda 1, so it doesn't really matter. Okay? So this is how you construct the polytope. Let me do one more maybe. So here's the icosahedron again, but with frequency order. This is the usual order that we like. In this case, if we want to average the second and third eigenspaces, then we have to convexify this bottom part. Okay, so take the vectors in the bottom part. We expect a 5-dimensional polytope with 12 vertices. But if you look closely, you'll see that all the vectors are doubled. So this vector appears 2 times, this one appears 2 times, and so on. Okay, so the vectors are doubled. So you end up with only 6 vertices and a 5-dimensional polytope. So that's just the 5 simplex. Okay, but there are 2 elements sitting at every vertex. So every facet has actually 10 elements because there's 5 coming from the facet of a 5 simplex, but there's doubling going on. So there's really 10 elements. So the complement is 12 minus 10, which is only 2. Okay? So the designs in this case have size 2. So as soon as you change the order, the size of the design changed, and here you see the design. Okay? So this is the recipe. And this doubling is pretty dramatic. So for example, in this next example, which is the truncated tetrahedral graph, if I look for an extremal design, meaning I want to average everything except the last eigenspace, now we expect an n-gon, right? We expect a 12-gon. This thing has 12 columns. But if you look carefully at this picture a little bit more, you'll see that every column appears 4 times. So instead of getting a 12-gon, you actually just get a triangle. But every vertex now carries 4 indices. So if I want to get a design, then if I want to get a minimal design, I look at a facet. I look at the indices that are complementary to it, which is this, 2, 5, 8, 10. And here you see the minimal design. Okay. So this is the theorem, that there is a polytope that organizes all of these designs. And now using this, you can do various things. So, okay, so before I go any further, let me just say one word why this works. So the proof behind this is oriented matroid duality or Gale duality. So if you've seen it before, then all we're doing is using this dual set of vectors. So I want to average the blue ones. The blue ones are really the eigenspaces that I wanted to catch. But it turns out that what are called positive circuits in the blue side are exactly the positive co-circuits on the pink side. So there's some duality going on, and that's really what's happening here, okay? So usually Gale duality, so Gale duality is actually quite old, I recently discovered. It's actually due to Strom from the 1800s. They call these associated sets in classical algebraic geometry. But in the world of polytopes, it really appeared in the work of Perles and Grunbaum. It's written in Grunbaum's book. That's the main place. I think that's one of the older references for this. And typically in the polytope world, people use Gale duality to find interesting polytopes using the blue side. So using what's called the Gale dual, okay? For us, the designs are living in the blue side, and we're using the polytope to tell us about the designs. So we're using Gale duality in the reverse direction to say something about the designs just by looking at the combinatorics of the polytopes. Okay. Right, so now once we have this theorem, we can get various consequences. So let me just summarize the different consequences. One of them is, of course, this structure, this polyhedral structure. This allows you to put bounds on the sizes of designs, because if you have a polytope like this, it has dimension d, then you know that every facet is at least a simplex. So we know that it has at least d vertices on it, which means the design is at most n minus d in size, okay? So that's really Carathéodory in action. It's not a very fancy statement, but it puts a size on the design, but it also shows the existence of these non-negative designs for all values of k, okay? So this was not known before, that they exist, but this proof will show you that. And the other thing that it does is it puts this sort of adjacency structure on designs, right? Because designs are sitting on the facets of the polytope. So you can take the edge graph of the polar polytope or just walk along facets and you get this graphical structure on designs themselves. So here, for example, is the Peterson graph. This is just a local picture. So this is one vertex of the graph, and then here are the neighboring vertices, and then sitting on all the edges, you see the non-minimal designs. And this goes on. Okay? This is just one vertex picture. And it shows some interesting things, like you see, this is a combinatorial design in the middle, but it's surrounded by non-combinatorial designs. So you can sometimes get these disconnected parts. Okay. So that's one consequence. And another consequence is this allowed us to actually do some optimization. Because once you have this polyhedral structure, you can study the polytope and then tell which is the smallest design. So we did this for 3 families of Cayley graphs, because one of the difficulties here is to know the eigenvectors when you want to do families of graphs. And not a lot is known about eigenvectors. So lots of people know lots of things about eigenvalues in spectral graph theory, but eigenvectors are more rare. But for Cayley graphs, they're okay because they come from the characters of the group representation. So we know the eigenvectors. So we did it for some families, like cocktail party graphs are the same as edge graphs of cross polytopes. So that one was easy. Cycles are also easy. Graphs of the hypercubes, we don't know the final answer. We don't know what's the optimal extremal design in frequency order. But in this case, what really helps is the theory of codes. So you can show, for example, that Hamming codes are very good designs. And there are some some generalizations of Hamming codes that are also very good designs. So these are all just linear codes. They form very good designs. Here, the polytope theory was not that useful. It was more the coding theory that was useful. Okay, so you can optimize through this method. And then lastly, the last application I want to mention is the work with Stefan. So this has sort of a small but kind of cute application to random walks. And so here's what it is. So if you remember how you do a random walk on a graph, we start with some initial probability measure. Let's call it mu0. It starts in one vertex, let's say, and the walk starts to move. And as you move, you get other measures. So at the kth step, you will get a measure mu k plus 1, which is gotten by applying AD inverse to mu k. So by iteratively running AD inverse, multiplying AD inverse many, many times, you propagate the walk. And then this fact here is very well known, that the distance between the kth measure and the uniform measure or the stationary measure is controlled by lambda 2, the second eigenvalue of the graph. Okay, this is a classical result. So you can ask, okay, what about all the other eigenvalues? Are they just completely useless, or do they have something to do with random walks? And it turns out through designs, you can extend this theorem to all eigenvalues. Okay, so here is what the result is. So it says that if you pick any k between 1 and n minus 1, then there is some initial measure that is supported on at most k vertices. So instead of starting with one vertex, allow yourself 2 vertices or 3 vertices or k vertices. If you do that, then you can always find an initial measure such that the convergence rate to the stationary distribution is controlled by lambda k plus 1. Okay. So for example, and what this measure is one of these positively weighted k designs. So if you start your random walk on one of these designs, so here's an example. So in this graph, for example, there are 18 vertices. Lambda 2 in absolute value is 0.75. So if you started the usual random walk, it would be controlled by 0.75 to the k. But if you take another eigenvalue like this one, lambda 11, it's only 0.25. And now the theorem will say that there is some vertex set containing 10 vertices, such that if you start your random walk there, then it will converge at this better rate. But it turns out because designs can have smaller size than the expected size, you can just start on these few vertices. I think here there's just these red vertices, 5 of them, 1, 2, 3, 4, 5, 6 of them. So if you start on these 6 red vertices, then you'll get a random walk that decays at rate given by 0.25, okay? So it extends that theorem to all eigenvalues. So you can imagine, like, again, in the bipartite graph, the random walk doesn't usually converge. It just jumps from one side to the other side. That's because the second eigenvalue is -1, whose absolute value is 1. But if you go to lambda 3, which is smaller, and you're willing to start on 2 vertices, then it will converge, okay? Yes, yes. So, I mean, you'll have it, yes. So this just comes from the general theory again. You will get. So in this one, we changed I changed a little bit, which I put under the rug, because now we are actually integrating eigenvector by eigenvector, not eigenspace by eigenspace in this theorem. Okay, so it's a little simpler than doing eigenspace by eigenspace. Yeah, so that's basically Farkas' lemma. So there's a little lemma you can prove that there always exists a measure that's going to be orthogonal to the first k eigenvectors. So that was Farkas' lemma. And yeah, it was very interesting writing a paper with the analysts, because for them, Farkas' lemma was really hard. And for me, everything else was really hard. So anyway, it's Farkas' lemma, the existence of such a measure. And so, but once you have the measure, then you can put it together in this theorem. Okay, so that's the last consequence, I think. Here's just a picture of a big design. It's from this article that Catherine has in the notices. Yeah, we were just looking for big data, and here's one. And that's it. Yeah, so these are the papers that I talked about. There's also this gallery of designs. If anybody is interested in contributing, please write to Catherine. It only has combinatorial designs right now. So there's many, many interesting questions to work on. Okay, thank you.
So there are bounds for the size of a spherical design, for instance. So do you also have some sort of bound for an optimization bound for the size of a graphical design?
Yes. So it's basically so that the bound is given by the existence of the polytope. So the polytope facets index the minimal designs, right?
Yeah.
And the relationship is complementary. So if the design is W, then V minus W are the vertices that live on that facet. That's the index set. So because if I create a d-dimensional polytope through this process, I know that the facets have at least d vertices on it.
Yeah.
Right? So that means the design has at most n minus d elements in it.
Yeah,
so that's the bound.
But this okay. So, but it may be difficult to see how many things you. But I mean, like there is no like easy to solve optimization problem like for a spherical design that you can just solve this problem and it gives you a bound that you don't have to know this polytope or something like that.
So you don't even need to know the polytope because the polytope is gotten by convexifying that pink matrix, right? Yeah. And because that's an eigen, those are all independent vectors, the dimension of that polytope is just the number of rows of that matrix. You don't even need to construct the polytope.
I see.
So the bound is easy. It's really just Carat-Theodori if you work on the blue side. It's just telling you that there's a cone, and if you pick a point in it, then it needs at most dimension many things. So that's easy. But what's not known is basically how much smaller you could go. You could have much smaller designs than that bound. And it's actually NP hard to check whether there is a smaller one.
I see.
But it can exist, much smaller ones, like we saw in the icosahedron.
I was thinking more of a lower bound actually, but we can.
Yeah, lower bounds can be trivial.
Yeah.
You could have just one vertex that can integrate quite a few. Yeah. Again, if we go to combinatorial designs, it might all change. So I'm talking about the mostly non-negative designs. So there it's really linear programming with the sparsity thrown on top. But if you go to combinatorial designs, I think you'll get non-trivial things.
So there's some non-existence result that spherical 7 designs don't exist. But here, I guess you can have these extremal m-1 designs. Is there some bound that says when the number of vertices is bigger than a finite number, those also don't exist?
No, they always exist.
They always exist.
Yeah, but the combinatorial ones not.
Okay.
So that maybe, I don't know if that's the right analog, but the positively weighted ones always exist because the polytope exists. So this was the fact that helped Stefan figure out this random walk thing, because without that, he knew that there's some measure that could have negative and positive weights that will do the right thing. But now that we know they always exist, that you can actually do it for a probability measure, not just a signed measure. So the positively weighted designs always exist for any k, but not combinatorial designs. And that I don't know much about either.
Wait, so do there exist combinatorial designs in the hypercubes? I'm sorry.
Yes, in the hypercube they exist all the way. In any ordering of eigenspaces, they exist. The extremal ones exist.
Wow.
So there cannot be anything that integrates all eigenspaces except the full set of vertices. That's a fact that you can write down because of the orthogonality of the eigenvectors. But you can ask for extremal, meaning that all eigenspaces except the last eigenspace. That combinatorial ones exist for the cube.
Okay.
Yeah. In any ordering of eigenspaces.
David behind you.
Yeah, to find the weights, do you solve an LP feasibility problem?
Yeah, it's essentially you have to solve an LP feasibility problem.
But it doesn't come from the theory, the weight. It doesn't say anything about it. Well, it just says they exist.
It does come from the theory, because, I mean, if you are willing to accept the oriented matroid duality, actually,
maybe.
These are all the slides I didn't want to show. Okay. Actually, maybe that slide is useful, the one for your question. Yeah, so here, for example, is Gale duality. This is something I skipped because I thought it would be technical. But here you see the polytope comes from convexifying these columns, and the designs come from circuits on this matrix. So that means minimal dependencies. So if you solve for the minimal dependency, that vector is the weight. So if this is u and I solve u times little a equal to 0, then that little a is the weight vector. Correct.
Okay, thank you.
So it is an LP, I guess. So Monique's question was whether she said that for spherical designs the weights come from orthogonal polynomials. and the points, the design itself, and is there a link to orthogonal polynomials? I'm not sure. So I don't know if the graphs are just completely different kinds of objects or what would be the analogous thing, not sure. I think what would be interesting is to understand some sort of limit theory. So as you let the graphs become really, really big on a manifold, does this actually limit to something that looks like spherical designs? This would be interesting, but I don't have any clue on how you do that. Yeah.
If there are no more questions, let's thank Rick again for the wonderful talk. And we have, your presence for today. And that concludes the talks, but we have a few more remarks. Do you want to start?
Yes, indeed. So this brings us to the end of this wonderful day. But please don't leave yet. I mean, there will be drinks very soon, but we still thought it would be nice actually to let also Ton explain us briefly what a CWI fellowship actually entails. So Ton will shortly say a few words, and then also Monique wanted to get the floor for a few seconds. Please, Ton.
Yeah, I think it's pretty boring when I tell you what a CWI fellow really means. On the other hand, so I felt like I can say a few words to you, basically, in my role. So I'm only director for 2 years now. And now I can tell you a bit about this fellowship. That is really, I already mentioned it. It's for people that have from CWI that have made an imprint on the subjects, the research that, like Monique here. And it has been said many times. And I must say also that what I sensed out of this, in this community knows its history and knows how to tell how things build up. And you played a role in apparently this Lasserre stuff and kind of getting, yeah, this, I'm ignorant, but I don't mind too much, right? These are the risks that you take. No, yeah. No, but I felt like really, so I'm a mathematician and was once also studying pure mathematics as a student. So, and this is basically, I recognize this beauty of building up. And I think what I sense, Monique, you have been a teacher and a supervisor, advisor to many people to help build this understanding from which youngsters also can develop themselves. So you don't plunge them in one go, this is, you go from here, but also probably have still told about where it comes from so that you build your intuition gradually and then you can move on from there. Well, we met when I started as a director 2 years ago. You were a member of the management team. And when you talk about service to CWI, I can assure you being a member of a management team is service to CWI. It's, you don't do research during the time you're an MT member in an MT meeting. Sorry for the abbreviation, but MT, because that's the management team. And it has been, well, first of all, you were group leader from, I wrote it down to be careful, 2005 to 2016 for the networks and optimization group. And then you got into the management team, and I think we can state that, I don't have to explain all the details, it has been a turbulent period over the last 5 years, I would say, and you have been part of it. And you are also meticulous on everything you do. And that also means that you have saved me several times on not making mistakes, but it's basically more service that you do because I don't do sufficient service, and maybe that was also happening with others. So it was very clear to me that when someone basically said, well, Monique, you stepped down as an MT member, this is also the occasion to to appoint you as fellow. It was very clear that should be the case. And a year ago, we came to your room with a bunch of flowers. It was really, really very small scale because we still Corona times. There would be a moment, and that's this moment, when we would celebrate. I offered Monique this CWI lectures, but I felt like as a present, but it was not much of a present in a way because you felt like, gee, a lot of work. Now I hope over the time that Guido and Daniel really took over. But also, as another example, you have to be aware this semester program, this is also part of, and the next 2 days will continue on energy as a subject. is of high importance to CWI because we really want to play, you're all many internationals here, but CWI is this Dutch research institute of the national, of NWO, which is the Dutch NSF or the Dutch Research Council. And we are really trying to play more than, I would say, more than ever is a bit too much, but really play a role in gathering people together from the Dutch universities, and hopefully then others come in. And the semester program is, in my view, the panacea to all of this. Because this is where we talk about research, this is where we engage, and this is where we get new results. And I think, yeah, it was really like you stepped out, we had this idea, and you immediately started setting up the semester program. So that was very important also, because we have really, I feel this is top-notch research, top-notch researchers that really work on extremely important problems. And you basically have put these people together. And I shouldn't talk too much, but so I didn't write this down, sorry. Then I need more time. But in any case, what I just wrote down, and that's what you also recognize. So I'm very happy that many of you really spent time of the presenters to say something about the contributions of Monique to the field, because I doubt whether she ever would do it herself. I feel Monique is what I call proverbial modest. I checked her homepage. Maybe you did as well. You won't find any awards. You won't find her that she's the member of the Royal Netherlands Academy of Arts and Sciences. You won't find her that she has been appointed CWI Fellow, but you won't find her that she's a Fellow of the Society of Industrial and Applied Mathematics. I found this on a Wikipedia page about you. And I don't know, but I'm sure you didn't make it. And maybe now, who did this? Did you, Lex? No, never mind. No, but I felt like, now at least we should know all this. So if you would know more about Monique, then you have two places where you can go to. Her homepage, for sure, for all the content. But also for the tokens of appreciation, you can go to a Wikipedia page. Yeah, I think I should stop here. Thanks for all your work on behalf of everyone of CWI, and also on behalf, I think, of this community, because you have broad shoulders that people have stood on. And well, I hope you enjoy, of course, the fellowship and further research.
Thank you very much, Ton.
Okay, so yeah, what can I say? I can only say that I am extremely happy. Thank you very much, Ton, for the nice words. Sometimes I felt like to look behind. Are you talking about somebody else? So, but I'm extremely grateful. It was a very beautiful day. I'm grateful to Guido and Daniel, who have organized this beautiful day. I'm grateful to the speakers who came here. 4 beautiful lectures. I think it was I have enjoyed them a lot, and I think it was enjoyable for the whole audience. So thank you so much, especially Amirali and Reka were coming so far, coping with the jet lag and everything. Thank you so much. I am grateful to CWI. I've been here now 25 years, and I mean, CWI is a beautiful institute and here I have found a great place to do my research. And I think this is really an institute which we should be very proud of, and let's do the best for CWI. I've been happy to work here as a group leader and then as a management team, in the management team, because indeed it's important work, and I'm very grateful that other people are now taking the work over and are doing it. So thanks a lot. I'm also very happy to see so many people here, so many colleagues, so many friends. I must say, very often when I go to conferences, I think, how lucky are we mathematicians that we may gather in a room and be on friendly terms, talking about science, thinking about problems. It's so great that you have, it's really something very special. So a whole other world is fighting about I don't know what, But especially nowadays, I mean, we are so lucky that we are having such interests which are taking our minds, and we are doing beautiful things. Sometimes it's maybe not applicable today, but hopefully it will be applicable at some day. And in the meantime, we have built up science and we have enjoyed ourselves. And I think more people are enjoying from each other at least, what the science which is happening. So I think it's a great thing that we have, and we should protect it, and let's hope that it. So I say all this because I want to. I'm really very happy to see so many people here, some friends and colleagues. It's so nice to belong to this nice mathematical community. So thanks a lot, everybody.